improve my learning myself and nothing more than that, and also to hopefully inspire you and make sure that you agree that it's a wonderful domain to be and you are in the right time at the right place doing the right thing, essentially. This is all part of our larger emerging digital technologies, and the part of it is this new next generation neuromorphic computing aspect. And my name is Uma Mahesh, and essentially what this is supposed to tell about me is that more than anything, that I am possibly qualified to talk about it, nothing more than this in this. Uh, Tells what I got to do at various times, means possibly being in the right place at the right time with right people, nothing more than that. Primarily in semiconductors from the beginning, being part of the India's first semiconductor company and passing through the Odyssey, and as it is going quite big, have a satisfaction that we have started that long time back ourselves and being part of it, continuing to be that. And more importantly, currently I'm the co-founder of Initera Nanosystems, which is a Netherlands-based company, and we develop neuromorphic processor. We developed among the world's earliest neuromorphic processor, the two analog neuromorphic processor, and this we have been at work for more than, actually speaking, more than 10 years, but officially more about 5, 6 years as a company. No, actually, company is more like 9 years, 17, 18, and so on. Here, the chip working, valued, respected, awarded. We have products coming out of it slowly and going to the next level. And in the process, we have gone through so much of learning ourselves, I mean, all the things. It so happens now that the world is picking up so much strongly in this area. So it's an opportunity for us to share essentially what we have done and so on. Now, primarily here, we are supposed to be talking about the neuromorphic way of computing. Now, from what I am aware and the context of our discussion, idea here is to introduce this concept, computing, neuromorphic computing, why it is required, how it is done, how we can all contribute to it and benefit from it. And in the process, so the way it is supposed to be addressed is by introducing the basics, concepts, trying to let's walk the journey through from the beginning so far almost quickly and see how it is being implemented now. So that idea is to remove any entry barriers for you or mental blocks for you, and most importantly, realize that it's an exciting thing. It's a wonderful course and a particular topic which upgrade is included in the curriculum, because what happens is many of you, if not most, the most of all, are in a decision making process in the middle and going to the next level and coming from various backgrounds. So idea here is to see when you make a decision either to do your work better or make your department, your team department or your company better, or starting something new. And it can be not just corporate, commercial, it can be regulatory missions, so many other aspects as well. So in all these aspects, how this technology can play a different role, impactful role, and how in future there's some of the technology have changed before. This technology of neuromorphic has a potential to be a game changer and enabler of a different future. And you are at the cusp of being a pivot, being the center of it. So when you make a decision tomorrow, either you make somebody do things, you can check with them and say, are you doing neuromorphic and how? Or if you are doing, let me try in neuromorphic, validate it and convince my company to possibly do more in that. It's essentially to give that confidence level and ensuring that you can plan big. That's the idea here more than anything else. And what we are not doing right now, and again, I say that I am part of this joy of learning with all of you. So this is just not, I believe and I hope it will be a initial first interaction of about 2, 3, whatever hours. But more importantly, it's a continuous thing. Tomorrow, when you have a doubt, you want to share something, tell me something. we can always discuss more because some of the topics we may not cover fully here, considering the context of the discussion. And so this is not only one. I would rather say this is a beginning one. That's what I hope it to be also. Please feel free anytime. I'm literally a 21st person all the time. So what we are doing here is that we said we're going to introduce you to it, make you feel comfortable and make you feel excited about the possibility and see how you will experiment with this implement it. What we may not do right now here is not going through extreme technicalities, say algorithms, how they are derived, more not in the engineering context, basically. What the pure classical engineering courses happen, we don't do that essentially. Also, this is not a workshop type of thing. We actually won't make you take something, implement a solution for a while and check anything, not at all. Also, it's not a selling of myself or a company or anything like that. The idea is to introduce the technology, show how different aspects are evolving in that, how things are happening. No, because the chips are available, workshops are there, all a separate one altogether for whoever wants to do and want excited by doing it. But currently, idea is to introduce this, make you give a sense of where things are and how things are and how it's going to evolve and what we can do. This is also that's why it is a very important structure of how the program is set up, and that's which is what we are doing. And the assumption also here is that many of you have not, at least through the current program, not gone through the AIs of the world, the neural networks, ML, the definitions of it yet so far, at least. That's a belief I have. So some of it, if it is repetitive to some of you, please kindly bear with that. And if some of it is too top level and not quite double clicking further, please feel free to tell me. We'll definitely touch base on it. If not now, later. That's the basic. Okay. So the way we thought we can do is most like we'll go through the basic concepts. What is computing? What is neuromorphic computing? Why it is required? How it is implemented, and what are the applications, and correspondingly, what is the road ahead, most importantly, because in the next 10, 20 years, you are going to be the leadership role and going up further and so on. And it's a very defining time. So what is not only technology, how it's going to further change and so on. There's also aspect we'll try to cover up over the next 2 or 3 hours approximately. So now let us, and again, at any time, please feel free to block me, stop me, because I may continue going on. I don't know about the break and other thing. Kindly bear with that. Feel free to tell me and guide me and correct me also. Okay. Now, essentially, all this we are nowadays we are talking about one of the big buzzwords we hear. In it is essentially transformation, digital transformation. We keep hearing this word a lot of time, and you, as a senior people and going to be leaders, are also involved in it. Either you're already told to be part of it, or either you're already part of it, either you're going to be told to make it possible, make it implement, or you want to. What exactly is this? Change is, from what it is to being different in various ways. That's change. And the transformation is a change which is more institutionalized, more embedded, more structured, so more long lasting, not changing for the sake of changing. It's more like embedding and becoming different altogether in a very positive sense. Transformation is always considered a very positive word of how to become even better in a systemic, structured, and lasting way. Now, digital transformation essentially means such a transformation happening through adoption of technologies which are primarily digital. Now, the reason digital is used is not because of any engineering or something, because in the world when we see around, whatever we see, we are only finally seeing a digital or an output which is measurable, tangible, hence digital. So while there are a lot of other technologies and reasons why it may be possible, when we are seeing something, it is clearly visible. When you see a TV, we see a TV image, we hear audio, we hear an audio, we see an image, we see something. That's especially digital. There's nothing like happening or going to happen transition type of thing, right? That's why essentially to make things easier to implement, particularly over the last about 50 years, it's a digital technology. It is called what you use, computer, phone, nowadays communication, then anything essentially, finally, what we see, though embedded, there will be a lot of analog, that is, a continuously varying factors or parameters. What we see outside is primarily a digital, means one clear, tangible look. So, it's a digital transformation basically means most of these technologies which are evolving are established already, utilize them to change the way, modify the way we are doing certain things, we as an organization, as an individual, as a family, as a society, as a company, and so on, and correspondingly do new things or do the old things better. That's exactly what it is. And when we do things differently, in that sense, what happens is it also means adopting technologies. What are more and more we keep talking about, we keep hearing a lot of buzzwords, and buzzwords are more common now than before because people want more faster return on the money, so they use the buzzword more. But use the same thing. For example, we hear the word cloud computing all the time, essentially, which means computing somewhere, which is compute. Somewhere happens because over a network we connected. It's like a computing over a network, which is what we had network computing for more than what 50, 70 years as well. But now in those days it was not called a cloud. Now it is like that. So names keep changing and IoT and all those things. Now in this era of further intelligence, when we keep hearing the two letters of alphabet AI and also ML many a time, and then we say how it is implemented into many things we do, same browser, same computer, anything, how it is changing. It's not just giving an answer for us to giving points is for us to make a structure. It is actually trying to connect it and give data to us, give more comprehensible data. Chat GPTs, Geminis, and so many other things, Cloud Air, many things are developed more and more, right? These are all various transformation means we are utilizing many of these technologies or products or solutions or services by somebody, or we are making them for somebody else also, but making them as an integral part of that. So you as a current and future leader we'll need to understand these technologies, understand how they're implemented or who does it and how, so that in what way you will need to possibly be associated with it, adapting to it or adjust to it, you can determine and use. That's the whole idea of the course as well. And that's also as a part of that is this neuromorphic thing we are talking about. So now, when we say this, let us try to begin with where are the things, how things evolve, and why the buzzwords we are talking about right now, like neuromorphic, are important. If you observe the chat, it has essentially a lot of technology names with different sizes to indicate essentially the how important it can be for the probability wise, and color wise possibly saying the timeline wise how it is going to be, when it is going to happen, and so on. So what happens is, take any technology what we are using now or we are going to use in future also, some have come, some have gone, some have come and gone, and so on and so forth. So when what technology came at what time and when it is gone or supposed to go, the prediction, this is this lifetime evolution of these technologies, not just means engineering wise, ways of doing all those things are important to know, so that either as a creator or the decision maker or the enabler or a supporter, you need to take a call on it. You can take a call on how to handle or not handle some of these things. For example, here we talked about there's a critical enablers, there's a productivity revolution, and there's a smart world, and there is a transparency and privacy. Essentially, four buzzwords and four quadrants, more like anything, trying to map many of these technologies to where they may be more suitable compared to others. That's what it is all about. So, if you see this, as we go away from the center, the time of it being at the peak in terms of requirement or adoption is approximately predicted. This is all done by Gartner, and for those of us who may not be aware of it, essentially, when you think of any tech, suppose tomorrow somebody comes to you, say, I want to use this technology, I want to make this technology, and you need to take a decision on it. So, one of the things you will definitely want to do or you will do is Where exactly does it fall into the picture? How important is it? How current is it? How hot is it? Or how cold is it? And so on. That will be very important for us to take the kind of decision which can be apt for it. Right. So when you see that, which for which you need to know. So any what you do is, if we are not, go to Gartner and check. It will give a history of all technology. Many we are not using right now. CD-ROM, for example. Okay, catheter tube TV for that matter, wired phone for that matter. Now, if you go back to Gartner's graphs of the past, it will tell how the technology has evolved, and it predicts when it's going to be the peak and it's going to come down and so on and so forth. So here, also based on that, if you see, is there any neuromorphic here? If you notice, it's on the right top corner towards the bottom, on the right to the right edge, almost at the border of the two colored areas. One is supposed to be 3 to 6, other one is supposed to be 6 to 9, which essentially means by about 2030 type approximately right now, this is going to be a peak adoption. So, but it doesn't mean it's going to start there, but it's going to be in a peak adoption in a reasonable size way, in a high probability way. So, what it means is, it also proves to you that this is a domain, technology and solutions according from that, which is going to be very important for us to be learning, be aware of it, to see how we can utilize it. That's essentially what it is. Okay. So now, the reason we I told you about this is the importance of the topic neuromorphic. So now
This
we
one
have
was the
sorry.
just had a question on this mass scale. Like when it's very high, it means by it's adopted by bulk of the population. Like what does mass mean in this diagram? For
Essentially,
example,
yeah, mass, we say, look at it, mass is the size of adoption.
size of
So not necessarily mean the quality of people called high quality, royal, nothing like that. Essentially low adoption to medium to high to very high adoption. What it means, Nasser, is not just it is being adopted at a particular time, also to what extent is it adopted. That's also important at that particular time. For example, if you notice in the top corner, top one in the middle, there's something called a knowledge graphs. If you see that, and it essentially says 1 to 3 years may it is there, but the adoption is rather medium. Now, what it can mean is, for understanding this kind of thing for any technologies, what it can mean is, of course, that maybe after some time, it may actually become higher adoption possible for some of them, or that may be the maximum, it may vanish also because some other technologies will come. Right. So, we used to have, for example, CD players, how things have a video cassette player, CD player, things have evolved, right? Technologies have changed like that. So, essentially, what it shows is the extent of adoption in a particular size. That is essentially, for example, if you see the right bottom curve, essentially, if you look at right side bottom one, on the right side, you have intelligent
Doctor, excuse
application.
me. Doctor, excuse me, sorry. Is it
Yes,
possible, please, to use the pointer, the laser pointer, just to follow?
I'll have to find one, but will it be visible to you if I do that? I'm not sure.
Yeah, but when you say the left, the right, it's. I cannot see it. I don't know
If I have
on the
one,
graph. Yeah.
this, I'm not sure. Uh, I will open find. So please forgive me for that. Maybe I should have done better. I'll make a note of it, sir. I don't know, it's not there right now here. Please forgive me. The right
Okay.
bottom, if you see the intelligent, that is above the productivity revolution line, there's intelligent applications and generative AI. If you see those things, okay, and the size of intelligent applications is quite big, almost in the very high zone, whereas the generative AI is in the high zone. What it's saying is, in the next 3 to 6 years time frame, these are the, that is the time when it is made. It's not made today, it's about made 2 years back. Those are the adoption possibilities, it's saying. Okay, so what it means is the adoption possibilities predicted at that time, and after that it can become even bigger or even smaller. That's it depends on the other factors also, not just alone only on that. Okay, that's important to realize. For example, interestingly, extending a bit to the left bottom in the smart world part of it, there's a digital human and AI avatar. If you see that, absolutely coming out almost, it means it's almost saying closer to 10 years type of time frame, and essentially saying, okay, it is there. That's going to be picked up at that level. And the metaverse we hear about, you see on the left bottom part of it, the metaverse, all those things we hear, right? While we say no, it's showing how it's going to be much bigger. These are all the prediction levels. I urge people to go through the Gartner's multiple, so many charts, analysis, reports, and other things which tell. So it will always be good for all of us to go through them. So it will be aware. Supposing you have an idea, for us to check what is the lifespan, because the same question your investor, your seniors will, decision makers will ask also about that. What is the timeline? How is going to happen, and so on. Okay, sir. So that is the idea. What we are saying here is how neuromorphic computing is a very promising field for all of us to be in. That's essentially what this is about, sir. Okay. So now, if you see, we'll see, let's, what is this neuromorphic computing and why we thought let's go from the very basics and work from that onwards. One of the first thing we keep hearing everywhere are the two letters A and I, which is essentially artificial intelligence. What exactly it means? All we are saying in the world right now is the current world can be characterized as, qualified as data centric. There's a lot of data, yes, and the data has to be processed. And because there's so much data to be processed, it has to be processed more efficiently and more intelligently. We call it, if you know, big data analytics, we call it big data, we hear all that, right? Similarly, essentially, from those things evolved this learning, machine learning, and artificial intelligence. What essentially it is saying is that intelligence which is as close to nature, that's why artificial means it's machines are doing, humans are not doing it. It is, they're not supposed to naturally do. That's why it's called artificial. I think artificial about it otherwise. Those are not supposed to be by their own original conception of them, they're not supposed to do it. But they are becoming more intelligent enough to either assist humans or support humans, or slowly with the agentic world, maybe they don't need humans in many of those. That also can get to that. That's another scary part of it. Is separate. So what we are saying is anything we do, it will be questioned how is the AI going to impact it? In the sense, either you have to adopt it or you have to create something for it. Otherwise, it may not be required. That become more and more of a norm now. So it's all more about how much of it you are doing, not necessarily if you are doing it all, right? Sometime back it was if, before that it was what, now it is why not? What else can you do anyway, right? That would happen. So it become more critical. So whatever we do, we are supposed to looking from the point of view of how AI will impact it. Means how you are doing or what you are doing, how it's going to be changed further by AI. Are you doing it right way? Are you utilizing it to do that way? So what happens? There are multiple types of AI, so that's another topic altogether. The point of AI here is it is there everywhere in all sorts of applications, any aspect of our life with extra intelligence is there because extra data is there. The data has to be processed to take some decisions because we can't keep on processing the data ourselves. We make the machines do it, and they make it and correspondingly try to give us some options, take a call for us to do it, and it's so on. And it increasing even more, ever more across all applications, more and more. So the way you are as you grew, when you started doing something to now, you already noticed how that AI part is changing. Very simple thing like web browser. Earlier we used to ask something, it used to give it data. Now it's going to decide for you. For example, earlier you had to go for a dinner, then you say, you say, for example, first you say hotel A, restaurant A, then it gives maybe the address of it. Then after some time, say what the restaurants, some will come. Best restaurants, something else came. And now you almost tell, I have 3 hours to eat and I want this kind of food, and they will come with extra questions to you or provide most of data why you should go, where you should go. Based on, they'll ask you further questions, your pocket status, your health status, your timeline and so many things and give the chat GPTs, Geminis, and other things are there, right? So what is being done before it changed so much? So if we are developing, for example, as a marketing person, or if you go to a customer, make attract a customer for that matter, how you even present your product itself has changed, and if you're designing, it changed. We keep hearing about coding no longer being there and vibe coding and so many other things, right? So things are evolving. It's going to be what we are seeing is not even the beginning. There's a lot more things, but more importantly, how that has come to what we see AI or the net result is what we see now. Like when you type something, what restaurant do you think I should go? And it asks you certain questions and comes with answers, is all happening with AI. But that has not happened there itself. That's all what you see is a much top layer. There's a lot more happened from the bottom to top. And essentially, it is happening because there is something called as machine learning next level, we say. It's a sort of pattern recognition because it takes the inputs and tries to data is collated, and from those patterns, it interprets something. That's it. That's where it is. But that came because it further has learned. Once you learn deeper learning, it's going to correspondingly that happens through neural networks. So learning happens. So correspondingly, you can create some patterns which are correlated, connected together to make intelligent inferences, which it tells. But all this is happening through a lot of data, which are essentially are called language models. So wherever you see there's a language model, there's a large, small, things are changing even more now, very targeted, specific and other thing. That means how much of the data set we are taking and analyzing. Basically, it comes to that. So this is how the things are evolving, language level models and neural networks, pattern recognitions, and intelligence AI. Which means for us to make these intelligent decisions, we need to be aware of how the neural networks, how things are. Suppose you have to make those decisions. You have to be the one who's giving those answers, not seeking the answers to go to a restaurant. Imagine you have to create something, hardware, software, system, firmware, system, anything, regulatory system, which essentially gives ideas and suggestions for something. Which means you need to, these are all the processes, and they one of the aspects of making the data and make it available for further analysis and dissemination is the neural networks part. So, but what are those? Neural network is a network is connection of 2 points. Okay, line, multiple points, you can say, call it as a network. Now, neural network means network of neurons. What are neurons? Neurons are supposed to be basically the fundamental cell of a brain. The terminal, the synapse, say, a neuron, I think where the processing happens is a fundamental cell. You can take it as a road, that's a neuron. So a network of those are the neural networks, and which essentially means the brain processes the data how by connecting certain neurons inside, and correspondingly something is remembered and we keep it. So that kind of neural network is what is making the data possible. So we are creating them artificially. That's why it's called artificial neural networks. But what it means essentially is a lot of data is there. They'll all be compiled, communicated, and correspondingly, they are given out based on certain activation. But more importantly here, not all the data is essentially given equal priority or equal weightage or equal preference. So there's something called a weightage across, and that weightage is the one which is called learning. So when it is asking a question, do you want which type of food? Do you want in which area? Earlier they used to ask, remember? Now here instead of asking, it tells if you are in this place, you go there, tell me which part of the thing you are. So it's essentially determining the weightages. The weightages are being determined by the system, and corresponding those are all compiled together and given a result. That's how the neural network part works, and depends on the data and how it is processed. The type of neural networks will vary. We'll touch base upon that. So now what happens is, so this is the data, you collect it and correspondingly take a decision. So now the dendrite and synapse are the equivalent in a normal brain language. So what we take a particular transmitter, receiver network, and that's the equivalent of that. So that is what happens. So we try to create those brain equivalent of the circuits, hardware essentially, and correspondingly which makes the software happen, which will determine those things. So finally the learning is identify these weightages and and keeps learning that part. That's how these things work. Now, the neural networks are there in many varieties, and as we speak, they keep changing. Means some other old ones may be fading away. That's how the evolution is. Some other better things may be coming along. Right, but it happens. So multiple varieties are there. In the sense, what application we are using right now itself, our mobile phone, for example, our TV for that matter, our camera, everything is at the end of the day processing the data in a certain way, and which means that's a connection of the neurons in certain way. Hence, it's a neural network based convolution. So many things are there like that. So each one is supposed to be good for a certain application because the kind of network it is, which means that kind of application or inference will that is good enough to use that network because it need not be overly complicated or overly time consuming or overly power consuming, right? That kind of thing. So, for example, that's how it is. So, which what happens is, and multiple things go on. The things are evolving right now to further and further. There's no end to it, strictly speaking. So now to see some of the examples is there's a feed forward neural network, which essentially means, but the reason we're telling it is all these are going to evolve to why neuromorphic computing is required. We said how things are evolving and transformation and how AI is happening and corresponding means how it requires neural networks and so on. That's where we are. So essentially here what it means is the data goes from one end to another end, just for forward going only, no need to think further in this, which means very simple targets, for example, can be used in a very easier way for that matter. Voice recognition, some identity of recognition of an image, and so on and so on. Because you're essentially going in one way. Your decision making is not necessarily based upon giving feedback, that feedback improving the input, and that kind of things are not there. So very straightforward, feed forward neural networks. So what we are saying here is if you are a software developer, you need to think what kind of neural network I will adopt for the data I have. This is an example of trying to do that. Then one of the most important things is the convolution neural network. What is a convolution? Convolution is nothing but two shapes are combined to make a third type of shape. We know in these waveforms, for that matter, when there is a square, and typically in engineering, we are taught two different shapes, for example, are combining together, and by they are added or subtracted or multiplied, a new shape comes, right? The waveforms we say like that. So essentially, convolution is taking the current inputs and correspondingly giving certain weightages to it and informing if we became coming with the next level. That's a convolution is very commonly used one. So wherever you see image recognition, object recognition, these are all typically used by convolution. One of the most commonly even in mobile phones also, we have this convolution network-based algorithms and software is built and put there essentially. So what a mobile phone is doing is when you look into it, for example, it takes the data, your image for that matter, your voice for that matter, like Alexa's for the world. And on that, they process the algorithms in this way, convolution way for that matter, some time, or AC feed forward somewhere, you determine what is to be done. And sometime, as the times evolve, the algorithm itself keeps changing also. Now, there's another thing called recurrent, for example. Recurrent is nothing more, you get a feedback basically. You take a data, you need a feedback for it. So, in fact, what we are saying is when you have to achieve something, you will need to have an awareness, right? Okay, what it means, I need to give a feedback, or how I need to have the data, will have certain idea, right? So then correspondingly, that's how the network work. For example, in the language translation and text classification, all those things, this recurrent part is used. Okay, so important here to say what we are showing here is one more thing. Nowadays, technology is so far ahead, even you don't need to worry about what neural network model I need to use. Again, because of all the intelligence piled up into the system, it itself can tell, you know what, for this you try convolution, or if you really want to achieve it for this kind of scenario, maybe there instead of convolution, use SOMA and so on and so forth. So the system is also assisting us. We don't need to worry about it. So we are trying to make you aware what kind of things are there. This is what I'm talking about. Self-organizing actually a bit of complicated ones. So essentially, you have a certain data, you further infer it and do take a action, take a call further on that. For example, you are at traffic signals. Then there are traffic signals. Some have less crowd and some have more signals. So you have to, which side you have to enable green, red, and so on, right? Which route you need to enable. So you look at it. And similarly, in a bank or in an aircraft checking in for that matter, if you stand there, which counter you go to. Suppose somebody will be there, you say go to counter 4 and counter 6, right? Depends on the people next. Now, supposing it is done automatically, as it is already happening, then how the system typically will tell is, okay, there are 3 people, there are 8 people here. So the next person should go to the 3 people side, 3 people counter for that matter. But imagine the 3 people person suddenly got stuck for various reasons, various variables, their passport, visa, ticket, extra luggage, so many lost something, so on and so forth. On the other hand, in this, each one is becoming 5 for that matter. So which means that will recorrect itself, reformulate and tell, you know what, you go here instead of that. As in sort, as a, I would say, very crude example of how this up higher dimension coming to a lower dimension and so on. Just an example I'm giving there. Point here is visualize the data basically and correspondingly see how the data has to be processed. So for some of these things, the weather forecasting and so on and so forth, and the patterns, right? This kind of neural networks are there. Again, the idea here is not to discuss neural network, go to the neuromorphic part. What we're trying to say is how different neural networks are there, how you decide which one to use when you develop a particular product, software, a program, or a system. We're giving an example of those. So don't think too much about it. We're trying to introduce to that. Now, example here, the CNN we talked about, right? So image recognition is one of the best examples. I said mobile phone uses it. Okay, and there's a in for image compression and so on and so forth, for example. Okay, so what's important to keep here, my recurrent neural network, which is speech recognition, means you say something, it remembers, you say something again, it has to go back and reflect, map it. Oh, this is that person's voice, right? That's right. It's a recurrent, it needs a feedback. Point here is, you don't need to worry about it because
Sir,
the system
excuse me, sir.
Yes, sir.
Sir, one very basic question, sir. Sorry, I don't know if people have asked earlier.
Please.
So the LLM and the neural network, how are they typically connected, sir? If you can explain that a little more simpler from a non-business background, non-technology background, right? Because the organizations today, we decide whether to go with OpenAI or with or Google offerings. Okay, so the that connect, do we even decide? Organizations get to decide the underlying neural network, or just to understand that part, please.
So what happens is, basically LLM is nothing but collection of data. Lot of language model it's called. Model means they put in some structures. Okay, that's essentially a lot of data. Now, if this data by itself doesn't mean much, from the data we need to evolve towards an answer, which means you need to then process the data. Right. So then only it should be used. The data by itself has no value, right? So you have a data and you have to process. So for example, I would say images for that matter. Okay, images of the people. So now there are certain images, and then correspondingly, based on that, you take a call. This is important, for example, image not necessarily in the people for that matter. In the agriculture part, if you look at it, when is a particular flower or a fruit is ripe enough for to be plucked and correspondingly sent to the market for that matter. It's an image recognition, right? So then what you're doing is you're collecting that data, all those images are with you, correspondingly, then you take a call, for example. Now, and similarly, the language model means a collection of the data for a particular area. Typically we use internet to we let all of us reflect back to ourselves how much of our internet data seeking is to what geography. So essentially, it is more of the data we seek are essentially in our nearby immediate domain or within the same ecosystem, basically about 60, 70, if not more. Very few will go much later, much farther, and very, very limited will go to a lot more, right? So the large language to local language model, you can call it. For example, in India and other societies, it can be a local language model also. Why should it be in English for that? That's for that. So LLM is purely data gathering. But once the data is gathered, what do we do with that? The data moving to an AI decision making, there's a process, it can't just be done. So that data has to be processed. And from the processing, you get some patterns, and those patterns, you interpretation, that's how it goes to the artificial intelligence, right? So when the processing happens, how do you process the data? So it is processing the data. How what depends on what applicable, what is the end expectation you have is determined by the enabled by the neural networks. So hope that is clear. The neural networks essentially make you have the data LLM which is with you, make it more useful for decision makings later. So neural networks is the way that data is processed. For example, you take any of these for that matter, right? There's a data going in a certain way to certain output. So it is that data is coming from the language models. And so by applying on the same data, depends on the end question somebody asked, one of the different neural network models may have to be utilized for that matter. And so that's why the neural networks, in a way, we can say, is taking the data, making it more useful for inferring and decisions by the next level to going toward the AI. Hope that gave some thoughts, sir.
Yes, sir.
Hello?
Definitely.
Yes,
Yes, sir.
that's
It
part
did.
of.
Thank you.
So like
Thank
that.
you, sir.
So what happens is, so similarly, the multiple applications do multiple things here. Okay. So now, if you see, typically in the sense, take any mobile phone for that, make it easy for us to understand. There's adaptive battery. If you need a battery power, if your power is going low, essentially it's a CNN part of it. Okay. And now, why is it a CNN? If you see, if you look at also ask questions, right? What is CNN? We say convolution, we said, right? CNN means, what did we say? Convolution, a lot of things are there, right? Going in various ways, this way. Right? Why is for battery, it is CNN? Whereas, say, for example, there's a different ways of doing it, if you notice, because the power consumption is from different applications running in a different way in a mobile phone, different usages of it. So you need to collect the data from them and correspondingly overlap them. Okay, and then the captions and the face recognition, most of these are CNN, but not always. For example, simply a voice command, you do Alexa something, and in the phone you do some voice command and do it. That's more like simply the recursive thing, because it remembers your voice and does something. This is an example of the neural network model. So what happens is, as you ask the question, the data is available. For the data to be made into a useful decision, some of these neural network models are used for developing the algorithm and correspondingly the software for it or the application for it. Just an example of these things, by the way, keep changing. It's not written in sand. As the complexity increases, as the power increases, sometimes what happens is we choose a certain neural network model because the available power is less. But better batteries coming, you say, I'll do more intense computing with a different neural network also. What we need to remember here is it's an evolving process, but on the data to make it useful for decision making, you need to process the neural network. That's how the thing works. And now there is a spiking neural network. What is spiking neural network? This is for the brain-like performance. So far, we are talking about all the networks part of it, right? Spiking neural network is more like how the brain functions. This is among the latest of the neural networks for somebody who is going to research on it and know about it, and or do a next level software development and so on. Essentially, what it is how the brain works. If you see a brain, we talk about neurons and say how much is the brain size and so on a bit later. It doesn't work all the time in the same way. The data is gathered to certain level, and then it's almost like you have liquid being poured into a container. Only after it gets full, it overflows, right? Or if there's a container which has an outlet, till the water reaches the outlet, then only water starts coming out of it, right? It's something like that. So spiking neural networks are the way the it's how closest to how the brain functions. So most of the neural network concepts are right now going towards the spiking neural network, very, very early days, essentially at the end of the day. And it takes its whole, and that's what is going to be the key for why the neural networks and neuromorphic processes are improving. For that matter, the difference is the same one before. We showed the same one before, but the difference here is in the spiking, we almost have it like a digitally converted. It's almost like a digital conversion of an analog one, essentially. Okay. And also the terminology wise, this becomes a synapse, and then there's a different neural network part of it we come to later. But spiking neural network is essentially making the data function more like a digital way and taking a care on that. Okay, and which is essentially going to improve the learning abilities. If you see, there is a conventional machine learning model, there is a brain-inspired computing, and then the competitive computer architecture. The world is evolving to where our spiking neural network can be more influential in these decision makings of how networks are to be processed. More importantly, across the world very soon. Now, this again shows why it is more efficient than many people, because spike means one triggering of a certain level, right? Basically, this is too detailed one. Just imagine that efficiencies are there across, depends on how you implement it. But more importantly, what exactly it means is, if you look at any brain, what it happens is there is a data which comes from somewhere, and then it is processed and gone to somewhere. So in the brain terminologies, it's called dendrite and axon. Dendrite is almost like a transmitter. It also can be a receiver. Axon is basically like a network. So one transmitter can be other one receiver and so on. So if you see this, basically, what happens is the brain has neurons. The neurons have dendrite and axon. The terminology, again, don't worry about that. It's not a medical class, but it will say how things are evolved. Important thing is they are unidirectional. Okay, and correspondingly, the neurons will be taking it from the after a certain process. That's the synapse, and those words come into picture. So this is another example of it. So there is a transmitter, there is a receiver, we call it. Right? Strictly speaking, if you see on the neurotransmitters, we see how the data goes between them. And it's a synapse which is equivalent to data gathering part. Essentially, the axon is like a network. It takes over. The reason we are saying it is when we map it to a real world, we need to map to the brain, which is how the spiking neural networks will happen, which is how neuromorphic process will happen. That's a more efficient intelligence can happen. That's the background of it. So here, see, for that matter, in the middle, you have the design. If you look at this part of it, right? The neuron, this is actually the brain, how it works. The dendrites, if you see, they essentially are gathering the data. They're all our actual neurons, how the brain functions essentially, if you see that. And they collect the data, and correspondingly, there is the axon, which you see the pipe through which it goes to the next level. Okay, so what happens is, if you see particularly here, is that the there is any hardware in a system, there's a software and there's a hardware, right? And there's an algorithm and other thing. Depends on how the neurons gather the data and act. That itself is an algorithm type in the case of a brain, how the brain functions. There's no real hardware separate and software separate, right? What it means is the dendrite, the neurons which collect the data, right? So correspondingly, how much the data is given, what weight, that's why they continue to learn. There's so many neurons in a human brain, not all of them work all the time because there's so much learning involved in that. And that's why the algorithms are essentially built in it. And that's typically. But now, see, the left part of it is essentially how we create that artificial neuron we are trying to create, where we are talking about right now. In that sense, what happens is there are algorithms and there's a hardware. So if you see here, there are a lot of inputs collected the data. This network also we saw in the neural network definitions, right, in the earlier slide. So what happens is the inputs coming, they're all gathered together, given certain weight, and some actions are taken. Now, when they're gathered, they're not just simply taken in the linear, uniform way. They're taken in a way where based on the application, the requirement, the target, the weightage for those will be changing. For example, you ask, I want to go to a restaurant, tell me right one. Now, the weightage for food choice is important, or the distance part important, or the cost part is important, for example. So the weightages will vary correspondingly, and those things are all again coming from the software and then the hardware part of it. In the brain, essentially, it is learning by itself. And we know, for example, we take the same call in the brain, right? I think I'll go today. I don't want to eat this kind of food. I'll go to this place because it's closer to where I am, and so on, right? So the hardware part and the software part, essentially algorithms are built in the dendrite part and of the axon part here. Whereas in our recreating the part, we need to have the algorithms essentially also add the weightages. That's the interesting part of software making the hardware more brain-like. That's a part of the neural network. But again, this is for your awareness more than anything else. You don't be that part of it. The same thing here. If you see, The top one and the bottom.
Sir,
Top one is
sir, I have a
yes,
sorry,
yes, sir.
sir. Is it okay
Please,
to stop you like this and ask questions, or do you want us to
please,
wait?
please, anytime, all the time, please, sir.
Okay, sir. Sir, typically, in that whole circle, this is the deep learning aspect, right? So the sort of a replacement of the brain in terms of the system digitally replacing the activities of a brain, right? And um, if in the end goal, okay, AI is supposed to do what a human being will do in normal circumstances, right? In terms of actions. There are two parts to it. So, in terms of if you look at, this comes from this slide where in the biological neural network, it's a gradual process of evolution. Okay, but when this is transferred to a system at this point in time, there are two aspects which I'm probably oversimplifying it, which are required for the system to understand. One is data, right? And the number two is the human behavior that also has to be understood by the system. Okay. If you look at a human being, in fact, not as a person, and let's say I'm in a manufacturing space, okay, there are a lot of things, me as a person, which I'm dealing with on my personal side. Okay. Okay, what I bring to the job is only a set of processes and activities which I need to perform. Okay, so that side of my behavior and data is not available to this vertical, right? So how can that be to the manufacturing vertical, which I do in my day-to-day job? Okay, all right. So how will that be complete in every sense, even over a period of time, unless there is cross-pollination of behaviors and data between the two domains?
So, question is, if I understood correctly, where there is
Yes,
a
sir.
lot of data and there is a weightage given to it as a factor, right?
Yes.
So, in your company itself, for that matter, in a particular shop floor, for that matter, there are, and those factors may change based on the particular requirement of that analysis. Is it, for example, to decide a product should be done or stopped, or a human being to be recruited, a machine to be bought, or so many other things, right? So based on the target requirement, we ourselves as a brain are assigning certain weights to certain factors which are different than the same weights we assign to the same factors for some other decision making. Right. So that's how the decision makes are done by a brain. So similarly here also, what happens is when the data is given, it is that weight part of it is trying to learn and learn. That's why the weightage part, what you see there on the left side, those are all by the learning. That's why the actual learning is happening for it. And that happens because of course, it takes a decision and it gets a feedback and it continues to improve. That's it may not happen one time. Over a period of time, it becomes more efficient. So what the way from the data, that's why that learning and assigning the weights and how they're depending upon the additional data or the previous data is how the neural network algorithm which will be utilized for it will be determined, and correspondingly from which how the output will come to us. Hope that
Got it. Yes, sir. Yes,
that's,
sir.
that's so it continues further. And now if you see here, same one, what we're trying to show is what we're achieving in real life with all these things are essentially trying to map the real life. Okay, and in the brain it's called synapse and the neuron and the axon, dendrite, all the terminologies we use. In the real life, we create the same thing. There's a transmitter, there's a receiver, and there's a network, and so on and so forth. And more importantly, there's a chip finally. It's the brain which is doing all the processing, and there's a chip which does it. This essentially is a neuromorphic chip. Because when we are mimicking a neuron, mimicking a network, mimicking how the brain takes the inputs and maps them and use less weight, more weight, and keep improving it, so on. Similarly, that also means the chip should be functioning like brain. That's why chip should be like brain. That's why it is neuromorphic process. That's why neuromorphic processing is becoming important, because that essentially is enabling. So what happens is brain is the ultimate processing engine in terms of most efficient power-wise, most efficient power consumption wise, both highest power in terms of computing, lowest power in terms of consuming, right? So that is the brain, so which is, and also all these neurons and so on and so forth, remembering and programming it and guiding them and so on. If only a chip can be done, which actually is like brain, because when you're talking about AI, learning and remembering and improving and so on, we're essentially wanting all systems to function like brain. Which means why can't the chip, the brain chip also is required to make like a brain? Then only it becomes easier. Else what happens is all the software systems are trying to function like brain, but chip doesn't quite think like brain, which means either you need a lot more processing and a lot more time to do it. That's why the processing is coming. That's why it's called neuromorphic, morphing the performance of brain. So now, if you see, the reason we gave all this is now going back to, we started here with spiking neural network, right? Which after we talked about all the other networks, then we came to spiking neural networks. And here, and we tried to say why spiking neural network means how it works. Then we talked about the brain part. So now we look at the applications of it. We saw applications for all of the other ones, for example, right? In spiking neural network, typically it's all about taking a data, analyzing it, and like brain and doing it. So think of any application, the SNN-based algorithm, and hence SNN algorithm-based software, and hence systems which are running on the software which is based on SNN-based algorithms are going to be all across in any of the applications, more and more than ever. That's the reason. And it is independent of the chip. The chip can be, by the way, digital, chip can be standard chip also, but the algorithm, how it will work, is building in more learning into the data, is the spiking neural network for the developing the software part of it. Yes, after this, once you start developing applications and algorithms in SNN, you also will say, why can't the processing be also in SNN? It will be much more easier for me. That's how the neuromorphic processing happens. So, for example, in healthcare, okay, image analysis, for example, which is more important. In finance, essentially improving fraud detections and all those things which are coming along. Of course, we have in entertainment and name it anyway. So Sir is talking about shop floor and other thing, right? Supply chain management and so on. How predictive maintenance of the machines, the industrial IoT equivalent and so on. It goes on. Transportation, again, our autopilot cars are coming, the signals are coming, and so many data are there. So all these are essentially are more and more algorithms written in SNN right now. Again, simply because it's almost like a very obvious thing. Brain is the more intelligent part. Anything, all these works are done by us before, ourselves sitting, assuming no computer, assuming no network. We used to use our brain to make these decisions ourselves, right? Similarly, so make a brain-like decisions. That's how the spiking neural network with applications will be even more improving and further evolving into much more complicated things becoming easier. So we talked about how CNN, RNN, and augmented, how they're all giving different applications. With SNN, you can actually do many of those applications, but you can also do some newer ones which are not quite possible at the same efficiency. Anything can do everything almost, but the time it takes, the cost of doing it, and the other cost means not just the price, is about the space, efficiencies, power, other things also come into picture, reliability, and so on also. The SNN applications are essentially there doing all over the things. So what we said now is, so far from the beginning, we talked about why transformation, artificial intelligence, how it means we need intelligent processing of the data, which means we need the data has to be processed like a brain. That means neural networks way of doing it. What are the different neural networks? Why spiking is coming more and more? And when the spiking happens, how it's going to be more efficient? And then we saw it's because it works like a brain, neuromorphic, neural, and other things. So with that, essentially, we are essentially, it will be good to possibly have a computing or a system, electronic system, hardware that is, which is built upon the fundamentals of the brain, so that more intelligent, efficient systems and solutions can be made. Which means we need to also look at how the computing architecture correspondingly evolves. If you see this, yes, sir.
One basic question. When you say spikes, can you just explain the concept of spikes versus continuous data with an
Yes, sir.
example, if you don't mind?
We will see it a bit later also. Essentially, as we said, it is not a continuous spike, is more like a digital. Okay, so it is not processed all the time, but only after a value crosses a threshold. That's a spike for that matter. So, for example, let us say water is in a container. It doesn't come out always unless there is an enough outside outlet for it, right? Till then it doesn't happen. So spiking means instead of processing it all the level, let it come to a certain level. Like in digital technology for that matter, those of us who are familiar with that, they say a signal will be of a certain value, current wise is 0, until the current goes to a certain level, then it becomes a 1. Spike is that.
Got it.
Spiking means basically instead of having it only the same time, it only changes after trigger, which means instead of processing all the time, you only process certain level. The negative of it, as we see later, means there's a certain assumption being made, definitely, no doubt about it. Okay, it's not like real audio masters, real connoisseurs say that nothing more than an analog music compared to a digital one, right? Like that. The moment you're digitizing it, your compromises are there. But because you're not processing all the time, you're only doing when a threshold happens, it's efficient, and more importantly, it's more power efficient as well. That's the reason it is. I hope that gives some idea, sir.
Yeah, that's helpful, sir. Thank you.
Now, if you see, look at
Sir,
the computer aspect part of it
sorry,
to understand
sorry,
this
sir,
more.
for
Yes, sir.
interrupting. So just one question, because I'm trying to associate this with the where exactly this neuromorphic technology is used. So because in our last classes, when there was an example of driverless cars where it has to identify an object and instantly take an action on that to avoid any collision. So so is that the processing which which is required to instantly make the decision? Is that the place where the neuromorphic technology is going to be used a lot, or is it something because till now from your PPTs and the architecture, what I see, it looked like very much parallel what AI is delivering, but here what I see, it's completely different in terms of the reaction time, which it takes a very less time to execute, because that's how our brain work, right? So is that my understanding correct, that in driverless car, which is I'm taking very visible example, where the latency needs to be very, very low and it should take an action instantly. Is that the use case where the neuromorphic technology being used?
You see, actually, the autonomous vehicle you talk about, it's just not only the latency faster, it's also the accuracy of the decision is also important. Both are
Yeah.
important. So, and it can be vehicle and so on and so forth. Yes. So, when you need to do process, think like this, forget the hardware part right now. When you need to have such a data, you need to process it, and you need to process it accurately, and fastest possible decision has to be taken. And mind it, the hardware actually takes longer to react, even for a software input, even if it comes faster, which means it should be even more faster for the hardware to act reasonably faster, right? So, yes, what happens is, in which case, in the autonomous vehicles, yes, a neuromorphic also is going to play a bigger role, not from the power perspective, mind it, because car has no power issues, the battery and so on, nowadays solar and other things are there. But importantly, yes, with the neuromorphic means that because how quickly you are reacting. So how do you recognize a human being for that matter? Is it a human being or is it something else? So there's a pattern of human inside. Right? So the algorithm, first of all, will be based on a neural network type of thing, because it's an intelligent decision. If any intelligent decision is being made, the algorithms are typically based on certain neural network based one. So yes, it is neural network. Now, which means any neural network can do that much more faster and better on a native processor like a neuromorphic processor. So yes, neuromorphic can be playing a lot of role in that. But it also means currently what happens is, I'm jumping again a bit, but neuromorphic right now is being used as we develop applications more for the within the car scenario, not the outside the car scenario. Within the car means your comfort, your control, and so on and so forth, but not necessarily outside, because automotive, the chips have to be automotive qualified, and all those things are extremely rigorous. They take a lot more time, understandably. So yes, that's going to happen also. Yeah, it's more and more. Also, what happens is the chip sizes may need to increase. See, brain has, we'll talk about that a bit later. The size we need to increase for it to be more accurate, more quicker. Also, because car also means, take an example, sir. A camera in a doorbell or in a room, okay, it's doorbell. The cost of it is less, the power available is less, and so the for it to recognize it is you who came, that decision making taking neuromorphic chipper can be very small chip. But same one, it's recognizing a human being there in an automotive. It can be, it has a lot more power. It needs to do a lot more faster. So essentially, what happens is you need a much bigger chip as well. So it will be neuromorphic chips, but it can be bigger chips of the next generation possibly. Hopefully, that gives some answers, sir. Okay, sir. So now, if you see, essentially in the computing architectures, for those of us who are part of it will know, it's in a computer family essentially has a processing engine, the data to process, and the data to store. So there's a data to be stored somewhere, and there's a processing engine. And in the processing engine also, there are two type of processing. One is you're actually processing the data. Second one is telling you what you need from the data. Okay, take these two numbers and add. Take to these numbers and subtract. Processing is doing adding and subtracting part of it, whether it should do add or subtract, and to do who is the control part of it. So what happens originally, the memory used to be single common memory for both. That's how the original architecture started, single memory, which is good, but it also means the timing of processing used to be slower. But later on, to make it faster, the memories have changed. There's a data memory, there's instruction memory separately put. So while you are processing one, you can get the other data. You're not waiting for the both things to happen. Earlier, what used to happen is you say, okay, I need to add two numbers. First, fetch data. You fetch, then you add, and you give back. It is taking 3 cycles. So here, what happens is data is ready. You say add, data is ready, directly put it in next cycle itself. So that's the kind of centralized one to separate memories is the Harvard architecture. But further evolving, it is not stopping there, but the computing is no longer the same the way we look at it. Because the data is earlier constant, static, or later on it was less evolving, less changing. But now it's instantaneously changing in our era where everywhere there is a computer. So earlier, long time back, if you ask how many computers are there in a room or in an office which to sell certain things. Now each person is carrying computers which are possibly bigger than, more powerful than big building, multi-story buildings about 20 years back, not the skyscrapers of 50 years back also for that matter, right? So much of data is happening all the time within a mobile phone or within a gadget with the sensors being there everywhere. By the way, sensor means mapping a physical condition to an electrical signal, which can be then processed by all these gadgets to make inferences and some actions to be taken on that. So which means we are talking about data which is there everywhere on the way, which means the computing can't necessarily be same as before. Because those were paradigms made for almost constant static data, almost with the processing to be done for decision making and implementation for later levels. It's almost like a decision being to done right now here in the room versus it can be done later for the thing. For example, you enter a room, light should turn on. That's immediate decision to be taken. So now, AC to be turned on, immediate decision to be taken. You can't wait for it to go somewhere and take. That's why the decision has to happen there, which is called edge now, the closest to the data center. But in the morning, say if 100 people come into the office at the same time, then correspondingly, in the multiple floors of a building and if a multiple buildings, thousands of people, that turning on and off what will actually has more magnitude of impact for that matter. So what it means is that decision making is happening at a bit farther. So there's a local decision making and there's a farther decision making. And so each of the local decision making will again need to be further done at the global level in terms of accumulation. But the decision has to happen immediately faster at the local level, which essentially means and communicated faster. So nowadays, computation is becoming communication. Both are going not only communicating locally, communicating over the network to somebody. Two type of communication, and hence the new architectures are becoming even more important than before. to make sure you do more efficient processing of the whole thing. Another example of it is, you see, originally we used to have only CPUs in any computer main processing unit, right? Data processing unit is called CPU. Then see the right one. Then we say we're processing the data for a particular application. Like we started playing games. So that's why it's more like processing the pixel level. That's why you have NVIDIAs of the world come into picture called graphical processing engine, for example. So in any chip now, any computer, you have CPU and then the GPU. But then there's another one which came along, which is called network processing unit. You need to process the data of the network data in certain way. So more are adding. So the processing itself is evolving and changing. What we see is not a today's change. Over a period of time, we continue to evolve the processor and so on and so forth. So now it doesn't stop there. Processor is okay, multiple processor is okay. My outputs are varying. Earlier, processor used to give find some signal on the computer screen and we do something. But with the data, with the output, the decisions can be light on, some water, some door, some alarm, some other thing happening. The whatever actuators in the sensor language, they're all changing for that matter. So things are evolving in the way the processing unit and the interfaces are there is continuing to change. Also, for that matter, earlier we used to have these interfaces, what are the network interfaces, right? So then standard so we connect the ports used to be there, RS-232, then we have USB, and then things are evolved. Infrared, now we have Bluetooth. Remember, everywhere something there multiple interfaces are coming, and those are all changing. So when all these things are changing, along with the processor, multiple things are also changing. Now, for example, the same NPU, it's called a neuromorphic processing unit is doing the other one. So what's happening is no longer a single type of data processing, it is evolving across the spectrum. So what we're trying to see, that's how the architectures themselves are evolving. Just not today, the neuromorphic continuing to evolve. Look at other one, it's an interesting paper also we'll provide you, how the computing paradigm is evolving over a period of time. So many of us will know that one of the best things about electronics is the only domain possibly where we continue to utilize our experience or enjoy far greater amounts of output, flexibility, convenience, and joy at far lesser sizes and even far lesser costs, right? That's in the electronics part compared to anywhere. Now, all these things are happening because the multiple changes are happening. One is, for example, the materials themselves are changing. What kind of materials are there? There's the silicon, there's the CMOS, then there's gallium arsenide. So many other things are coming, blah, blah. But one of the changes of that. Other changes, the architectures of the computing itself, how the different architectures are there, how they're evolving. Computing for that matter, there's a configurable computing, there's a reconfigurable computing, multiple things. Don't forget about the buzzword. What we're saying is a lot of changes are happening. But in addition, the basic computation aspect, how you compute the numbers itself is changing. We all know, for example, about quantum thing we're talking about, that is entirely different one. And most important thing in this is that neuromorphic, the green one, that is the neuromorphic is the way. So neuromorphic way of computing is now picking up, evolving to be taking more important role, and which is also established because of the reasons we explained, how more data is happening, it's happening so frequently, so unpredictably, and we need to take decisions which will affect a lot more, so not just unique decision, lot more surroundings and other ecosystems and so on and so forth, which essentially, and also it needs to make more inferences. Not every decision needs to be left to the user to make. We need to make a decision also the machine has to make, artificial intelligence, all the things are happening, right? Hence, as you see in the paradigm also, the neuromorphic is picking up a lot compared to before. This is showing basically that how neuromorphic computing is evolving, why it is becoming more and more important. So hence, what we said here is computer architecture is evolving from Van Neumann to Harvard to other aspects to neuromorphic. And this neuromorphic is also becoming important because there's the neural networks, neurons, and that's implementation. That means AI, which is essentially required for transformation. That's why we have been coming to understand why neuromorphic computing is required. And if you see that how exactly it is there is neuromorphic, if you look at it, this part you can see engineering. There's a neuromorphic engineering, there's a neuromorphic computing, there's a neuromorphic device. First thing is the neuromorphic engineering. Neuromorphic essentially means morphing the performance of brain, how the brain works, try to make your system or a software or a solution work like brain. So if you see the computing devices, neuromorphic engineering goes back to Mr. Carver made Professor Saab in way back in the early 80s. They did. So the research itself is a lot more, and it's going from there. And then based on which to achieve this, people started making computers. I mean, they make computers. It's like nothing to do with neuromorphic processor, by the way. The existing processor itself, you make an architecture which reflects the neurons you saw, right? Neurons putting them together and connecting together in network part. As hardware wise, you realize. So a lot of systems have happened which are supposed to enable computation like brain in the entire digital format. That's the next level. But Intel, IBM, we have Spinnaker, and so many things are there. Further into that is the neuromorphic device itself. It means now computer can be done on any processor, but that's a neuromorphic computer. But what's important is why don't we have a neuromorphic processor which will make a neuromorphic computer possible even more efficiently? Now, to make a neuromorphic processor, there are multiple ways. There are a lot of terminologies and buzzwords. It's just not a silicon chip. Our point is that there can be many ways it could be done, and things are also evolving. Finally, coming to a chip nowadays. That's how things are evolved. So, putting it this way, in the boat, Quadromet has essentially ensured. So we're going back to that emulation of nervous systems around electronics, but doesn't stop there. It's further, we have created a system, computing systems in the UK, how these systems can be made. The original thought was how the concept is, but further working to make computers itself, it is done that way. Okay, and it evolved from there. So now what happens is when it says neuromorphic computing, essentially what it means in the sense, computing like brain, how brain works. Similarly, computer should work that way, which also means the cells, the basic cells which make a computer possible should be like a cells which are like brain. That's where the neurons and synapses, those kind of things are coming. And that's how the things further evolved. So now, if you see one by one, look at what happens is the original platforms as Spinnaker and all the things are all developed, but things are further evolving from there. There's a wide consensus that neuromorphic computing is going to be the way the future is going to be there. And the spiking neural network is there, it's going to be taking to the next level, is the belief and how that's where people are going to work on. So now, if you see how exactly the neuromorphic computer is making the artificial intelligence, may actually make it more real. Artificial intelligence means computing and so on, right? So what neuromorphic will assist in doing is make it more actual intelligence, means make it more faster, more accurate, and more intelligent in terms of doing it by itself without waiting for feedback to improve. It can possibly perform by itself. That's where the important thing is. So that's how it's going to evolve. But what it means is essentially delivers ultra low power, because it's like a brain, not all of them are working all the time, and the spiking also a part of it, ultra low power. And it, because like a neurons, like brain, it enables learning, which is the adaptive learning. And because the way think anything how the brain works, multiple things keep happening in a brain, right? So because the way it is designed, one can keep doing parallel processing, and all this put together, neuromorphic essentially becomes more efficient. If you see this another way, traditionally, the architecture is supposed to be one human and sequential. Okay, it's a clock-driven architecture and depends on the memory processing and so on and so forth. And obviously, it's consume a lot of power and it's to happen. But importantly, in neuromorphic, what happens? It's a brain-based architecture, parallel, it's an event-driven spike. Because of its scalable easily, low power consumption is done and so on. But more importantly, the concept of edge AI, which essentially is where our neuromorphic will play a lot more role right now. But what is this edge AI? AI is artificial intelligence, that is, make things become more intelligent, work like brain. Now, what is the edge and cloud? For most of us are aware of it, but refreshing that part, essentially, any data we used to collect before and they were sent somewhere for processing simply because of a higher processing power. Remember, we used to have a desktop, we type something, it goes to a server there, which is to run and give the result back, more for a power. This basically is what that server can be in the next room, next building, or next country. Nowadays, it can be next continent, next planet also. That's one of the ways. That's a cloud part. But That's the cloud part that's important. But what happens is when the data is generated, if you look at it currently, we're all talking about data, which is data driven, which is data analytics, we say machine learning, we say big data, all those things, right? These are all based on, world is based on data. But where is the data coming from? Data is coming from the data sources, the applications, and which is typically called edge. So edge is where the action is happening in terms of data. So now if you see, edge is not a line. If you really see, more and more sensors are coming. If edge is like becoming like a band, so if you hold two hands in front of you, there's a left hand and right hand. The right hand is connected to the networks for the cloud and other things and so on, larger capacities. But the left hand is where the data is exactly generated, closest to the application, closest to the end user, you and me. That is called the edge. So all the gadgets we use, our phone, the room you sat in, the car you sit in, the place you are standing, they're all where the data is being generated as called the edge, where it is processed somewhere as the cloud part of it. But now, with so much more data happening, so fast, and with a lot of other things being dependent on it, you need to make decision making faster. You need to make decision making quicker and also more accurate, which means you need to think how I will possibly more intelligent decision more accurately, okay, in the fastest possible time. That's where the neuromorphic is coming. Hence, neuromorphic is increasingly more important and valuable for the edge devices. So for the any edge automation of the gadgets we use, phone, camera, light, temperature, anything you see that, that's where the edge-based AI is coming out of value. That's where, because of it, neuromorphic will be even more important than the traditional computing. Wait a minute. Does it mean, but I have my light off and on signal coming. Does it mean it's not useful? No, sir. It is useful. Currently, we have enough automation devices everywhere. Door opening, signal, alarm signal, light, AC, temperature, everything's are there. Definitely. This has been happening for a long time. In fact, I have the honor of making that kind of earliest companies in the world, selling it to Cisco and other things. The point here is, those days when you're doing, so currently all these technologies are based on devices which are done about 10 years back. But now what happens on that, you have to take this data and make intelligent decisions. You need to implement more AI algorithms. Will the current electronics make it possible? Answer is no, because the processes are not meant for that. It can do. It can do with a higher power, possibly more slowly, which may not be the right cover application. So what it means is, very soon, as we saw in the first earlier slide, the Gartner slide, very soon, about 2 3 years, you and I will be end consumers of intelligent gadgets, can be remote, TV, fridge, all these things, phone and other things, which are based on neuromorphic based devices, because that will be more intelligent, faster, and more importantly, is the least power consuming. That's where it's going to evolve. So for the edge AI, neuromorphic part. Now, doesn't mean it stops there, as we'll see. As the chip size goes by, as we already discussed, that this for larger chip sizes, maybe in future it can be for other applications also. But currently, as we speak, it is used for the edge AI very importantly. Giving another context of it, basically, when you talk about the brain and so on, why it's neuromorphic is at a particular one. If you see, a typical we has simply about what, a million type of thing in the basic cells, but a brain, human brain typically has more like a billions of cells, a billion neurons. I'll show somewhere else how the thing interestingly works. You have all the brain is billions of neurons, but doesn't work. All of them are not working all the time, sir. Only some of them are working sometimes. Not all of them are working on the algorithm. That's how the brain algorithms work. Remember, we showed the weightage it gives is automatically the algorithm hardware itself and how it executes the software. That's why the brain is a very fascinating device. So when you do a neuromorphic computing now, you need to see how many neurons it should have to work like brain. You don't need billions of neurons because brain is not using them. God made the brain with all the what you call redundancy and safety and support and like all the mechanisms, right? We don't need all that. But correspondingly, that you see how the with a small brain, the power levels it is consumed, and we see that will give a very fascinating story of how the power and those things are there. For example, how the time, how quickly it happens. For example, if you see, we said how the human brain and microprocessor, for example, if you see 3 to 4 micron, and the microprocessor has a 30 micron size and so on and so forth, what we're trying to show here is human brain is amazingly so efficient, and that's how the corresponding neuromorphic computing happens for that, which means the positive of it is low latency, faster and low power, very good for a lot of real applications, quicker applications, sensor fusion, that's with the edge data. But the other part of it is because it is essentially more like a spiking neural. It's not quite accurate, low precision. And which also means sometimes the variation can be a more. This is the other part of it, which means maybe for the highest accuracy ones, neuromorphic computing may not be quite right now. For it to be done, it needs to be a much bigger processor, much bigger computer, but much bigger neurons like brain essentially. If you see this again, the same thing, right?
One question.
Yes, sir.
One question, in terms of like in the earlier slide, you said the learning for this is real time as against like traditional AI, which is it needs a lot of training data and all of that. So question I had was, how does, if you're having this neuromorphic design in terms of computing, how is training taking place? You know, how do you, where where is the data going as far as training is concerned? In the brain, it's, I guess, based on memory, based on conditioning, all of that, and it's more instant. But with neuromorphic computing, how is training taking place? Because you
So if
kind
you
of
see,
real time.
look at this, sir. Any computer and any computer, any data, it needs to be trained, right? And to how to utilize it. That we saw all those neural network algorithms and all that, right? So that has been happening before, it will continue to happen. Tomorrow, something else also. The point here is the neuromorphic computer means is a computer architected to work like brain, which essentially means the efficiency of processing is faster in terms of speed and better in terms of power consumption. And the data with more clear difference is the spiking neural network type of thing is possible in a brain-based processing. Spiking neural network means, as we try to show how the algorithms work and how many more applications are supporting, a spiking neural network basically means we can have a lot more data processed in a more efficient way. So, how a neuromorphic is making learning better is because it is enabling new algorithms to be developed in a spiking neural network model, essentially. So otherwise, what happens? You think of the CNN and other algorithms; they're all important. Don't take me wrong; we're not trivializing any of those things, but they have a certain because they are continuously working on the data that's model compared to the spiking part of it. They essentially become that much more compromised in terms of getting the right result at the right time with the right parameters. So a neuromorphic computer essentially enabling one more neural network modeling, thinking that way. So which is opening doors for creating learning models and hence creating products which can be more efficient like brain. It's enabling those things. Hopefully that gave a context, sir.
Yes,
Because
sir.
primarily the earliest a lot of other CNN networks are there. It's also enabling something called a spiking neural network, enabling opening up an entirely new way of doing things. The process is more reliable and directly meant for it because brain, like neural networks means you need to have new understand neurons, which means that neurons should be there in a chip. That's why it should be a neural network. So by definition, epistemology, etymologically also, if you implement neural network, neural processor can do the implementation faster and better. Yes, somebody is asking some questions, sir. Please.
So just in terms of you said like this is a spiking network, so it needs to understand the threshold based on which it'll, create actions. So how is this, in the human brain you have like, I guess it's sometimes you can call it gut feeling or whatever, but it is establishing the threshold and it's acting based on that. How is this, neuromorphic network registering that threshold? How is it learning about those thresholds? Like, how is that training taking place? Yeah, I understand it's going to be brain-like, but what is the fundamental building block?
Fundamentally, sir, keeping the chip design engineering part on the side for another time, basically, it's almost like we are programming it to see how much data is coming essentially. So the more it is coming of a particular type, it's like supposing for each input, each person comes in, say, a shirt, you will do one tick. Each person comes in t-shirt, you'll put one tick. And when after 10 shirts come, for that matter, 10 t-shirts come corresponding, that 10 with equal to 10 ticks come, then you correspondingly tell the next level what to do. The spiking, you are giving instruction. So if that's in learning, you make it happen, you know this 10 is the number for that matter, you essentially told it. So similarly, when you're developing the processor, in the spike happens because the more it is coming, more data is coming to it. The more spiking is what? Essentially like a voltage level, right? So the more data is happening for that. Suppose or take a sensor, human presence. It coming from an analog sensor. What it means is it's essentially giving electrical signal. Sensor maps a physical condition to an electrical signal. So human being is seen. So that camera essentially gave an signal to it, one signal. But another person came, it's giving another signal. Means the signal what it gave before is increasing in strength, either in amplitude or in its width value, right? Correspondingly, so it goes to a certain level and it triggers. That it's almost like saying transistor turns on after a certain voltage level, right? It's almost like for this each person coming, for example, I'll give say 0.1 volt. So the moment 10 persons come, it becomes 1 volt and then the trigger goes essentially. So neuromorphic, the learning part and the triggering part is happening primarily from the inputs itself it receives, but later on, of course, you can also program it in a different way. Hopefully that gives it an idea, sir. Of course, we can go detailing separately on the chip design part of it, and that will be more clear in that sense.
Yeah, thank you,
Yes,
sir. Yeah.
So now, since this is an example of neuromorphic computing, don't worry too much about it. Basically, what we are saying is the computer is essentially same, or the interfaces are essentially same primarily. The processor is what it changes. And of course, the interfaces change corresponding to what is being constructed and other thing. So low latency, ultra power, if we have seen all this importantly, the more important things here is to say the algorithms part of it. Network structures and parameters can be configured, whether they can be trained better, okay, compare in the traditional one. And but the issue can be correspondingly, there's so much data coming that assumptions are being made that makes algorithms have to be improvised further. As you asked correctly, when the spike comes for that matter, right? Sometimes you need to possibly keep improving it and other things. So another way of just look at it, basically, is for parallel neuromorphic computing, does parallel processing, and let's say the parallel arrays are there, okay, and correspondingly it takes it from there and those parallel data it processes with a signal, it triggers to the next level using the neuron. It doesn't have the control unit and other thing. What is called it's analog, we make analog processor, actual analog neurons are there in that. Now look at the applications to make it more clear for that matter. So what happens originally, there's a mainframe and then there's a client server architecture we said it, some here, somewhere. Two, then we talked about locally mobile phone, the cloud and all those things. So now we're coming to the edge computing, edge intelligence. All the intelligence is happening more and more on the edge part of it. What does it mean? If you see essentially the earlier times were more like programmability intensive. Means you have a lot of data, you have time to understand, program and learn more and improve and all that. Whereas when you say it's an edge, basically, it is more of a cognitive presence, light, temperature, noise, pollution. Most of these are our body senses those things. Right? They're more like a cognitive factors, not necessarily computing factors. So in the current era, we are mapping the cognitive factors, and in order to address them, we have to have the computing done to address. That's why the neuromorphic computing. The earlier data is not based on cognitive factors. Earlier data was the raw materialistic data. But here, these are the current era, the edge data is more like cognitive data, and hence the cognitive data has to be computed correspondingly, and that where is the best processing engine? That's why it's in neuromorphic computing. So think of health monitoring, wearable, IoT devices, think of anything and everything what we use and see around us, remotes, all those things can be definitely usable with neuromorphic, and that includes consumer application, that includes autonomous cars and other vehicles coming and so on and so forth. In fact, we'll see some more application where a lot more bigger computer, those things also possible, but it's much farther. So if you see how neuromorphic happens, we saw how the devices have to evolve and what exactly it is containing in that, and correspondingly why it is important to do, because it performs like brain, it ensures the brain-like efficiency, it enables the existence of new network models like SNN. There will be more new network models also coming, and all the cognitive computing can be done much better in a brain-like fashion. That's why we saw the neuromorphic computing is coming. But now, what about the devices? So which means the computer, we saw processor, there's a memory store and other thing, the processor has to happen, right? So it's very important that these devices have to be created, neuromorphic processors have to be created, and they have immense benefit of, because they're working like a brain, they'll mean a lot more. But neuromorphic processor, we have to create a neuron and those kind of terminologies. They're not like the traditional adder, subtractor type of terminologies are not that. So there's an example of how they are done. It's just an example. We talked about neuromorphic engineering, which is neuromorphic computing and neuromorphic device, right? So here what happens if is an example of how various computings have happened over a period of time. Currently, we are talking about neuromorphic process. They're just now enabling and emerging, but it is there happening for a long time. In terms of computer, we showed about Spinnaker, we showed about Lolihi, Intel, and other things. A lot of things are working on. They're all trying to do neuromorphic computers based on not neuromorphic chips, but existing chips connecting together like neural networks, and write extra software will make it work like brain, mimic the performance of the brain, and then use it, which means they're digitally trying to mimic the performance of the brain. But it has one positive, negative, but that's how it has to be evolved before. That's how it is done, all that. So many people have done it. Like Spinnaker type of things are open. There's a brain project where people use them to create more applications and learn. All this learning in turn will improve the neuromorphic processing and the edge processing later. So these are Spinnaker, Intelloy, the brain project. These are all the various examples of how they've all started it long time back, for 10, 20 years back. It's continuously happening. How correspondingly they've done the neurons and other things, try to create them, how to make them realize, but in the existing chips and existing hardware essentially. That's how they have done all the thing, and these are all very well-known product lines and going on and do it. If you see that, for example, how if you see the original ARM architecture of the Spinnaker, okay, is about 0.01 real time to 10 times real time. Whereas in the ease of use case, the next one, the moment you go to Lolihi, and I think it's almost becoming 100 times the real case. But further, when you actually make neuromorphic chips and further, it will be even more better to it's 1,000 times a real user's case. So because it's like coming closer to the human brain. So by using this, the chip is becoming more like brain. So that's why the performance is improving. It's a continuous process. But important thing is when you look at a neuromorphic device, there are requirements and there are challenges. If you see, when you do a neuromorphic device, we essentially are making neurons and synapses are working like brain and connect. It works like event driven, the spiking and other things. When something happens, like a brain is seeing on the road, you're looking on the road, on the corridor. Suddenly you find somebody new and say, hey, that person came. It's an event-driven trigger. That's how the brain works. So similarly, neuromorphic process also have to work like that. And correspondingly, it's a lot of parallel work. So there's a lot of challenge in doing that primarily. Most important thing is, particularly during the edge devices, it has to be integrated to a sensor. Sensor and it have to work together. Data comes from a lot of sources. These are all extra challenges we need to meet. That's not easy, which means for you need to think differently. But of course, low latency, faster, make it better, efficiency, and there are the new things. So using neuromorphic devices, you can make applications which can be redoing what is done already with the older things. So whatever you see currently, in the edge level particularly, you can definitely do much better with a neuromorphic processor. Is an example. We'll try to show some examples and show it to you. This is a chip. We're talking, we're saying all those things, but is it really there? Is there a processor? Is it working? Is it the reality? How far away from the reality part of it? Because you showed that 6 to 7 years, maybe you can have the Gartner in the beginning and other thing, right? Yeah, the difference is while the original computers were based on digital chips and other hardware and boards and other things have evolved from that. And there are neuromorphic processors being done around the world. There are most of them are for a particular application. Like Prophecy does for a vision only, and different people do for a different application, like more like a neuromorphic processor for a particular application processor. But what in Inatera we took an approach is let's make a processor which is a generic processor, which will be for any application, depends on how you can program and how you run the neural network models and so on and so forth. So basically, we are trying to show that quickly, give an example of the practicalities because we have started talking about originally transformation, AI to make AI models and the neural network. Neural networks will require neuromorphic computing will require neuromorphic processor and so on. So now, is it available? And if so, how we implement? What are the examples? What are the real life cases? That's important. So this is an example of how sensors are there all across the world, and they are literally there everywhere, going up and down. You don't need to worry about things. Sensors are going to be happening. It's just increasing as we speak right now. But if you see the system electronic wise, exactly how is it? There is a sensor, the edge we talked about, right? The device, the gadget, and so on. Where each our phone, our wearable device, our watch, everything has sensor, room, and other thing. They're all sensors. Sensor maps a physical condition to an electrical signal. Now, that electrical signal has to be further processed. There's a microcontroller for it, and then correspondingly it becomes a part of a big system, and then it goes farther, gets integrated into it. If you remember, I talked about the edge level, there's a left and the right. The sensor is the left one because of the application. The right can be said more like the middle one, the gateway nodes and other things and so on. So what's happening is as we go away from the edge, the power consumption is more, power requirement is more, of course, processing is more, and all those things are there. But closer, a lot of people are working more in that space. So they get the data, they get processed. But the data, where is it coming from? It is coming from sensors. And sensors are mostly analog. So sensor data which is on the left side has to be given to them on the right side. And it can't be directly given. Somebody has to translate it. And that translator is what we are in a Ethereum nanosystem. We are essentially that microcontroller who map a sensor data to be processed by everybody. So it's because when you do this thing in the edge again, we said there is a challenge of a power, faster, efficiency, and all those things are very important. The other thing. So that's why it's important to make a processor which works like brain, so which was an analog processor. And we have been working it for a long time as such. Honestly, we have started a company in 2018. Because it's a part of our earlier company. We did this first IoT company processor way back in 2006 and sold it to Cisco among others and so on and so forth. So we evolved that further from that to the next level, making a microcontroller which will be available. So today, as we speak, we have the chip ready, available, working in the market, on which applications are being developed. So tomorrow, suppose you want to develop a neuromorphic application, you have the application kit available for you. Means the chip, the software, the compiler, the SDK, everything. You can just start developing an application. So wherever you see a sensor, where some automation is happening, that is based on electronics, which is of long time back, right? 10 years back. So in future, very shortly, as we also certified by the Gartner, you require new type of electronics, new type of chip, new types of automation solution, you can develop it. So for that, we have the hardware ready, including the chip and the software around that. We can develop applications. That is the neuromorphic thing we are doing. It's one of the earliest chips in the world, which again gives the power efficiency, faster size and everything. It's a 2.8 per side type of chip, and which is essentially supporting primarily the spiking neural network part of it. This is an example of the brain thing I will tell as we talk about how the brain functions, right? Now, we just shown to show that so many neurons are there based on a particular happening. Some part triggers, not all of them trigger equally, and most of them don't even trigger. That's why a brain of about 10 billion neurons is there, but though we hardly use some fractional part of 5%, 10% sometimes, and so on. This is how it works. So similarly, the neuromorphic processor with the smaller enough neurons also, because so many unused neurons are there, right? Similarly, in a chip with full used neurons can do similar functionality. That's the idea. What you're saying is you don't need a 9 billion neuron chip to work like brain for many of the applications, because it makes the software for a particular application, but smaller neurons can do. That's the idea, because ensure all the neurons are functioning. And this is the spiking part we talked about. Essentially, what is a continuous data based on the value we trigger it, encode, we digitize it correspondingly, and we process it. This is how the chip internal part of it. But more importantly, look at our microprocessor. For those of us who are electronics, it will be good, and for those who are not, also it will be clearing. The important here is all the interfaces which connects to the plant. But importantly, there is a spiking fabric, analog and digital spiking fabric, and a CNN. See this means we are supporting spiking directly internally. So we make a spiking neural network based algorithm data to run another thing. Our chip supports that. But in addition, as we saw, CNN is there a lot of ways, convoluted, right? That is basically mapping two inputs, combining them in a certain way to generate a necessary output. So we also support a CNN accelerator, which means you have an application already in CNN. You can still use our chip and get more power efficiencies, but you can also use our chip to write SNN applications, and correspondingly it can be work. That's the advantage of the chip we developed, and it is working and selling in not necessarily in great volume, because in much earlier days, currently the applications are being developed. More importantly, as some of you asked, the functionality of it. For example, we have tried some of the functionalities to be proven. When you do a processor, you show some applications, but then based on that, we urge the customer to develop applications and we support them. So, for example, the audio scene classification. You're walking. So you're from the conference room, you're walking to your office corridor and then go to the public area. And conference call is continuing for say 1 hour. The noise level is changing, so corresponding is the noise cancellation capabilities of your earphone should change. So, which means it should not function just the way it functions normally for uniformly, but it changed. That extra awareness is possible with our spiking neural network based neuromorphic processor, and you see the efficiencies. Similarly, sound recognition, who said what, and more importantly, we made radar-based gesture recognition, radar-based human presence detection. What it means is currently there's a camera. Camera will tell this person has come. Your doorbell, this person has come. But most of the places, camera is a violation of privacy, which is avoidable in many places. And more importantly, it also means more power consumption. So, can't we have human detection done through other things? Yes, radar is one option. We develop solution with radar, human detection. So based on the solutions are developed, other solutions are being developed, interestingly. So if you see this way, for example, the inference latency and the model, we see the modules is how small, 30 small model we get developed. It's about 150 size inference latency faster in a radar-based one. And of course, 40 times power consumption saving. These are practical real life numbers. So we have a chip on which we developed applications, we have solutions developed and shown. This is to certify to you that neuromorphic is delivering wonderful quality and perfectly feasible to work. So wherever you think of many of the applications, end use, whatever we all use, right? In all of those, which have electronics and microcontrollers, a neuromorphic microcontroller-based solution is going to be very much the order of the day soon. So if you're a solution developer, you can develop applications using a neuromorphic processor, take our board and other thing. If you have to make solutions for a customer, for that matter, you can start thinking of using neuromorphic and hence more intelligent AI algorithms. And if you are a regulator, if you are a system creator, you can think of how neuromorphic based intelligence can be used. There are a lot of opportunities are there that way. So now it continues in think of consumer electronics, IoT, industrial IoT, variable everywhere. It is going to be even more wherever there is a microelectronic sensor is used, a microelectronic controller is required. And where a microcontroller is required, a neuromorphic microcontroller can make it more efficient and strong and safe and secure, definitely, that part of it. But how is it possible? If you see, to make it possible for you, we actually provide you a kit, complete kit. We provide a kit for you, which is our chip in black in the middle, with a kit which works. Which works means for that you need a software ecosystem to develop an application so quickly, so fast. So you develop an application. Okay, so this is provided. All you need to do is start learning. We have support system built in, people directly actually supporting it to you. So if you are an application developer, you can develop applications on the neuromorphic. And if you want to have application developed for your ecosystem, incorporating them for your in your company, you can think of neuromorphic and use our kind of thing. I'm just giving an example of how easy it is becoming. Why is because remember I showed the neuromorphic, the Gartner and other thing, right? If you are currently today, neuromorphic is a business to business scenario, which means we make the chip sold to customer who are businesses. They make the gadgets, phones, computers, and name everything and anything, which will be usable by you and me later, maybe in 2, 3 years down the road. That is how the thing is going to evolve. This is an example of how things are changing shape quickly in neuromorphic. And it is a reality. Neuromorphic computers exist. Now, again, keep in mind, we don't go to a shop and say, send me 4 neuromorphic. The way you say, we buy 4 laptops, right? 5 computers, another thing, right? We used to say the servers, we say. Now, for example, when we go to a shop and say, when you buy a phone, we are buying a phone. Are we saying we are buying a camera? No. Are we saying we are buying a computer? No. We are buying a phone which has all this, right? So similarly, neuromorphic computer means they're not buying, give me 4 neuromorphic computer. You don't order like that. It's an embedded processor primarily currently in edge devices. That's why neuromorphic is an embedded inherent reality right now. Of course, very soon, as the sizes will increase, more neurons will plug in, more applications develop. As it goes right, remember the diagram I showed, as it moves away right from the sensor to the other part, it will, you can also start possibly implementing neuromorphic computers, but currently it is you buy a neuromorphic processor, by the application, a gadget, end-use gadget we develop. That's how the thing works. We are trying to show how exactly this works, nothing more than that. Now, it continues further. What happens is when you look at these devices, like show how it works and so on, the key thing will be how the computing use cases will further take. Think of first of all, we said easiest thing is talk at the edge. Smart city, healthcare, wearables, lifestyle, IoT, industrial IoT, anywhere and everywhere sensors are there. Neuromorphic process, microcontroller is used. In future, new microcontroller is being used. That is neuromorphic microcontroller, and that's a neuromorphic computer. So neuromorphic computing is available not because it sits on a desktop for us or a laptop for us. It's because it's inherently there in them built in. So the algorithms are developed that way. That's very important part of it. So audio recognition, speech recognition. The interesting is the robots part of it, how robots will work, how autonomous cars will work, as somebody said. Everything and everything you can essentially have wherever electronics is used, use a different micro, like we used to say, remember, faster microprocessor, right? Now we say more brain-like microprocessor, which of course is faster and more intelligent for that matter. And you think of an application, everything and everywhere it is there. More important thing will be when we have a neuromorphic processor, applications are developed. We showed how the neuromorphic processor is available for you to develop applications across the world. We are encouraging people to develop applications. Keep in mind, when you develop an application right now, it is actually going to be useful for across the world. It is one of those areas where the applications are required, but you develop in your country, it will be useful for everybody else also. That's an exciting part of it. So we saw how intelligence happens, with the AI happens, neural network happens, and then the corresponding you need a neuromorphic computing, neuromorphic devices, and neuromorphic chips, and how we are there. And it basically try to tell you, neuromorphic computing is not something you look at up there. It is integrated, embedded into everything. Currently, it is at the edge level around us, in a way, all of us. For example, sometime back we said how many computers are there, microprocessors are there. We to look at a computer or a laptop, say 1 and 2. Now there are more more powerful microprocessors in our phone. We don't call it a computer, right? Like that. So neuromorphic computing is going to be an embedded aspect of life everywhere. It's going to do that. With that, we also need to look at some of these applications one by one. And the important thing is, while we are saying it is edge, we are saying it is at the embedded computing, immediately you can ask a question, does it mean it stops there? What about the future part of it? Yes, future is future. Neuromorphic hardware for data centers is an experiment is being conducted, and for that there is a lot of work going on in that. We are also part of that research, and we did that part of it very well. What happened in that is, it's still a research level. Basically, a computer is put together, computer in the cards, right? You have all the cards. If you see that, there is a processor before, and nowadays you see the processor also, NVIDIA processor also will be plugged in, right? The AI data centers are coming. Basically, the pixel level computation part of it, right? The data is more cognitive, we said, not like earlier data, which means the processor also more cognitive processing. So there, in that processor, use a neuromorphic processor and make a small computer for trying out. This is what it is. So a lot of computers are tried one by one, how things are happening, and compared and other things. So what kind of chip is there, what kind of processor there, we looked at. So if you look at Inatera, the first one is also one of them beside that, and corresponding many of these are there. If you see how we do, for example, our Inatera thing is actually the CPU, and it doesn't really require training, it starts working that way. There's only 1,000 neuron one. There are also 300 neuron one. If you see that, there's 150 multiple. There's in fact a million neuron ones also there in Lohi. There's experiments are made. Why? Because to say how good, what size of neuromorphic computing processor may be useful for a data center. Basically, they're all plugged together. A lot of applications are run on it, essentially. So when you see, what was found out was the neuromorphic based computing is very energy efficient, and correspondingly it is performing quite better compared to a normal one. The energy is improving and the faster it is happening. This is a trial experiment conducted. So to show for anybody, is it there only for edge? No, sir. As we said, it's going towards the right. Also, only thing is the chip size will increase definitely. Corresponding the algorithms will change, another thing. It continues to definitely work better for all these aspects also. This is an example we are showing you to show how neuromorphic computing can overall later on be taken to much higher data centers and other things as well. We'll send you the paper part of it. The idea here is to show how this neuromorphic thing is going to be across, because there's a question about will it be useful in autonomous vehicles. That's how it will be. I said it needs a bigger processor and other thing, right? This is how it goes. The what you apply, what you see outside, and when you see a camera from a mobile, say the doorbell is a different type of what you call clarity or a fast and risk compared to one on the road, right? You need different type of process. The evolution is definitely there. Currently, neuromorphic algorithms, SNN algorithms are being used, and of course, internally it is being used as a thing also. Now, there are other aspects, other examples like this for that matter. This is a system done by an Indian company in Pune. This is a fire alarm. What is this fire alarm? Is the first ever smoke detection with privacy preserving. What does it mean? See, fire alarms, you have seen all that when something burns, the smoke comes, the smoke detector is there. Many of cultures are known that even if the smoke is of no harm, fire alarm rings and fire engines come under. Also, we have seen that, right? That's not. Why can't smoke be detected to understand what is exactly smoke source? So this company has actually developed product which identifies what the smoke source is. Is it cloth? Is it wood? Is it metal? Is it plastic? Is it something else? Which means based on that, you can take a call, okay, what is burning is this, so we don't need to necessarily take that kind of action. That's primary important thing is. And then it doesn't stop there. Further into it, human being, to this, we added our neuromorphic processor based device, that application kit you saw, right, which will detect human presence. What it means is we identify the humans being present in a place without violating the privacy at lower cost. So what it means is that fire alarm has human detection capabilities. So it will tell in this room, for example, there's a fire happening in a building, you as a fire brigade came, it can tell this room, this one is burning, this room wood is burning, this room has computers burning. So you'll say, wait a minute, wood is not important, let's save the computers. You can take a call, right? Now, that room has 20 people. Oh, wait a minute, that's the first thing to take care than computer. So you can make a more intelligent safety decision So this is a very valuable smoke detector, not quite there anywhere in the world, very, very early days. So that's an example of an industrial IoT edge device, which is made with our own neuromorphic processor. I'm just giving an example. Also to give you an idea that if you are making an ecosystem, a decision making, think that such products are existing, or you can make somebody, I need this kind of product possible with neuromorphic and other thing. And suppose you yourself are a developer, you can say, well, let me develop this neuromorphic thing. I know how it goes, and now let me based on that I can project, for example, that way. There's an example of that. But now, similarly, there's a robotics. One of the biggest one is the robotics part of it. They're going to be there everywhere, and we see all the gadgets working and other thing, right? But there is an intelligent robotics, not a big one, but can be useful for home and various aspects. So what happens when you use a robot typically is one will hit other collision part of it, okay, and other one is not necessarily responding in time, and of course is working well. So there is a various aspects of it. Currently they're all working on the GPUs and other things, for example, and correspondingly, why can't it be tried in a neuromorphic processor? So with and spiky neural network example. So I say still early days. Again, as I said, in about 2-3 years, you and I will be end customers for neuromorphic based ones. But today, the developments are already happening in the business to business model. So if you're starting a company, if you're running a company to doing this thing, you should try to doing a neuromorphic. On the hand, if you're a developer, you should develop in that. And if you want to, on the other hand, start learning and creating it at the right time, because very soon it's going to be big. If you see this one, on the right side, on the SNN basis, the success rate has become quite high compared to the other remote learning part of it has happened before. So this is an example of showing, again, real life examples we tried with our microprocessor to show that if you do something with a neuromorphic type of processor and SNN type of thing, it can be more intelligent, because again, it's working like brain. And similarly, the autonomous vehicle. If you see, we talked about how the autonomous car and other thing, right? The multiple ways, ADAS and multiple ways of security checking and so on and so forth. Because we use the processor neuromorphic in it, the correspondingly, it's all trial ones done, trial ones with the vehicles, but more like the laboratories and other things. The more you have a neuromorphic type of processor with spiking neural networks connected, which essentially making the ADAS even more autonomous, even more automatic and autonomous. It's happening that way. That's how things are evolving slowly. It's a bit early days for all of these things, definitely. When we ourselves don't see a what you call like video visible doorbell with a neuromorphic processor right now. Obviously, cars with neuromorphic processors and everything will take time, but as the question was asked, it is the way things are going to go further. It's also that's an opportunity for you. You as a creator, innovator, thinker, developer, even entrepreneur can think of, let me develop this thing with a spiking neural network, which will go with a neuromorphic processing for that matter, like that. And other important thing here is the wearable part. Most important, edge we talk about it, which means a lot of not only lighting and other thing, what we wear and carry and all around that. If you see that. If you see how typical it used to happen was, we used to plug in something, how we used to have our BP measured, something is connected to our chest, something is connected here, right, and measured. And then slowly those electrodes are becoming smaller in size, and they slowly get embedded into the chip itself. So it means that's why, so it becomes smaller. So what happens is, if we make a spike-based smaller sensor thing connected a spiking processor, like neuromorphic processor, what it means is it is going to do much more efficient and faster consumption. Variable will become even more efficient simply because spiking neural network, simply because it's a neuromorphic processor, and hence what it means is a sensor electrode, smart electrode can be connected as close to the chip as possible. Of course, there's always a challenge of which are with the chiplets and not how close you can integrate is always a challenge. That shows the footprint of the product, but it works. This is an important thing we show you. This is also not just a theory. It's actually a product developed in India with IIT Delhi, where what happened is they've been trying to do with multiple electronics, various people. Now, here, instead of that, using neuromorphic processor, the same muscle detection. It's called electromyography when you move the thing, right? When you move your hand, the muscles will be detected, muscle movement will be detected. Based on that, gesture will be there. Also, it will help and the arms and the medical circuitry and so on will be there. So they have done it. So it has proven very well that how the solution is very more. You can see the Inetera part working on this and other thing. How efficiently it is, how fast it is done there, and how it goes from there very easily. This is an example of how the neuromorphic EMG classification is done. It's an interesting thing we have developed, and it's working well now. We have also demonstrated in our CES for that matter. This is an example of how a muscle movement thing is done, developed for that matter. That's one by one. So many things are there. So we have shown some example of how a fire alarm is done, how a wearable is done, and we also talked about how it can be part of various applications from anywhere to the data center part and autonomous vehicle to our closest to us, including mobile phones and other things. These are very early days in terms of product being available to you and me. But as Gartner other predicted, it's a matter of maybe in the next 2, 3 years, we will have, you and I will be the end consumers. Currently, the customer for us are the companies. It's very much in place and things are going further. It's going in a very exciting fashion in that part of it. So neuromorphic computing is how things are going to happen. The processes are there, the systems are being, applications are being developed. So if one has to implement them, it's a good opportunity. Well, you are like an entrepreneur, you are a creator, innovator, researcher, and if you are actually service provided to somebody, you can make things based on that and do it. So there's a lot of opportunities are there. And we also said neuromorphic computing because it based on different, it enables different neural network called spiking neural network for that matter. And we also said spiking neural network is more efficient because it takes a particular threshold and does it. Also, essentially because of that working more on the neuron-based model, and we looked at various neural network models, how they work, how spiking neural network is better, and why neural network models are required. Then we talked about how AI can you need data, and then AI happens, which in turn is required for transformation going back. So from there we walk to here. Idea here is for us to know when you say here, okay, neuromorphic computing is here to stay. It's going to play a big role, make a big change in our life, and all sorts of industries and commercial and ecosystem, and even for governments for that matter, regulators for that matter. Things have evolved, technologies are established, devices are out, solutions are being developed. So it's good for me to start thinking in terms of making it either part of my ecosystem or my business plan or my options, and if I need it, how I get it done from others and so on. These are all the things to be kept in mind when we think further. So with that thinking further, we say, but what is ahead? It's not just simply, there are a lot more things ahead in that. First things here is we are implementing the ethical part of it. Sir asked about human being detection and so on and so forth, right? If human being is there, not detected correctly, whose fault is it? Who is responsible for it? That means it will where to use, where not to use, to it. Is it ready to be used for that matter? There's a privacy, there's a surveillance part of it, right? The cameras coming, other thing. There's a transparency of the data. It's true. Most of these are common for them when the IoTs and cameras, those things were there before, right? Only thing here, it just becomes even more intense here because what with the neuromorphic processor based electronics you can enable is because of all the AIs and others coming in even more mind blowing compared to before. You should be careful. So ethically speaking, there are multiple aspects one can think of. There is an implementation ethics, there's a manipulation ethics, there's a bias, there's singularity, autonomous system, so on and so forth. Okay, including robotic rights and transparency, many aspects are there. And there will be more coming. So what happens when we either as a developer or as a consumer or as a regulator, as a decision maker, it will always be helpful and valuable to think in terms of the ethical angle. And ethical angle is in a way one of the thumb rules we suggest is just ask, is it legal? If things are legal, at least half of the ethical thing is right away solved there itself. And you have to implement because these are all intrusive into our thing, like the cameras we say and so on. Neuromorphic computing will make it even more possible because battery life is reduced, it stays longer, so you can have it deployed in not many places and so on. As an example, and the application is enabling with the new AI is a new our data and other thing, right? So we suggest that to keep the ethics part of it in mind, correspondingly make a decision cautiously on that part of it. And then there are other challenges. The hardware, which is the number of neurons and how you build it for the what is the edge will have certain requirement, and correspondingly when it goes all the way there, it's a different challenge altogether. Still early days for that part of thing to happen. It's a continuous process. And then you also have the software. We're talking about SNN algorithms. There are new algorithms written on SNN. It's a newer neural network. A lot of people are trained on CNN and ANN and other part. So you have to train them. That's important part of it to take from there. And more importantly, there are real standards are not there quite here. And there are no real standards here, which is anyway good. That means any of us can try something. What is not so good is, which means what we develop also may not be quite pickable by others, may not be usable by others, right? That's a challenge. So when we also have to take part in either challenge, standard definition or standard being becoming strengthened, and these are all the challenges to work on. Sometimes you may find I did something by the standard, change the standard as something new. That's a part of the things we see always. But more important, those are the challenge, ethics part of it, hardware challenges, software challenges we saw. But now we see further. We saw our processor, we saw edge-based, we saw devices, we saw life-changing and all those things. We said how it can go further to the cloud and other aspects, right? But there are a lot more things on that. There is a concept like collaborative autonomous systems for that matter, which means each is an autonomous system by itself, but it have to collaborate with others. The data has to, because when you say AI is coming in, each one is intelligent by itself. Each one can even become an agentic AI by itself, but its performance also will be influencing the other system, or you need input data from the other system. Multiple things you have to work together for that matter. An example for that matter, if you see, it's the same fire alarm thing we're talking about for that matter, right? So when you go for a fire alarm thing for that matter, and then there is a humans are in one place, machines are in one particular place. So correspondingly, your system we should tell humans are there. You have to indicate to the ambulance system to correspondingly start coming. An example, the moment because things are autonomously intelligent by themselves, you need to possibly combine them together. That's a very important part of it. Concerningly, this is going to be there across everywhere. Collaborative autonomous systems are entities that can cooperate among themselves. Okay, it is going to be very important. Okay, so an important thing will be they should be able to perceive and understand their own condition where they are, dependably interact with the other physical world, intelligently evolve through the learning, take decisions, and self-decide the actions based on the other things also. So very soon in the next decade, this will be very important part of it. Collaborative autonomous systems are going to be there. So when all of you are going to be key decision makers and creators of the next thing, we cannot just think like only our device or our system, how each system will add to give data or contributing from that. So very important like self-inspection, self-configuration, self-adaptation, self-healing, self-optimization. These are all important. Depending on where you, for example, place it, there's nobody there. You need to self-maintain, give an alarm that I'm not okay for that matter, the remote alarm. I'm just giving an example like Antarctica type of thing and so on. That's just an extreme example. But here is you need to have a lot of self-capabilities built into the system so that in the real world we can essentially make remote applications and hazardous applications more better controlled, more better operated and done by us. That's why the collaborative things are very important. And other thing is something called living intelligence. If you see what is living intelligence is, intelligence, yes, living intelligence is there everywhere, it's integrated, you can't separate it out. For example, long time earlier we know of the era when entertainment was when we turn on a TV. Information was when we open a newspaper. It was a spike of it coming. It's a remote one in that sense. But nowadays, you can get music information everywhere, entertainment. It's all is a part of all that, right? So, for example, camera earlier is to bring a camera. Now, of course, we don't have that part of it. Camera is a part of your thing. Audio part is part of mobile phone. So, living intelligence is going across to the sensors and so on. It goes everywhere. So, living intelligence is going to be how a further innovation is going to be driven. So AI add sensors, add AI, and correspondingly, and make different solutions possible for everyone. That's very important. Okay, this is how will happen. The machines will be more intelligent, and because the living intelligence is there, machines can be cameras, can be alarms, can be even actual machines, cars, and other thing. So essentially, all this will require neuromorphic computing. So living intelligence, collaborative autonomous systems, they're all going to happen anyway. With the neuromorphic processor, they are going to be even more going to be reality faster and better. This is very important part of it. So without focusing, understanding these aspects of living intelligence and other part of intersection of how one will work with other, we may not quite be possibly be really missing the bigger picture, they say, right? We're missing how the disruption, the technologies happen, we will miss it across. So think like this. Importantly, reflect on it, ensure how, don't think of it as a single, say, alarm or a fire alarm or a muscle detection or something. Add it to the other ones. And that's how that you can make a much bigger solution, much more ahead of others, or make your organization much more better than others. Okay. So correspondingly, if you see, what happens is this, what we know is sensors are the pulse of all the digital technologies. Okay. And we know that every engine needs to be there, data, and the data is there, the AI is there, it's going to be there, working everywhere. So all this being happening everywhere, sensors are going to be there, more digital data is going to be there, and it happens. But further in future, what happens is companies continue to embed even more sensors, yes, even more data, yes, and even more conditions, like we talked about living intelligence, working, interacting with other systems, they're all going to happen. And hence, more the way that we talk about the data being more varying right now compared to before, right? It will be even more so because each data will be dependent on other conditions as well. The value of the data, that is the interpretation of the data is. So the evolving future will mean so many more changes are happening. So you need to think more intelligently, more fast, and enable more intelligent solutions. That's why neuromorphic computing is going to be even more important. So what happens is you are there, you are in an organization. So how do you position your organization for this very important part? I know you learned about technology. We talked about how AI happens, how it will require neuromorphic computing, with a neural network, neuromorphic computer, processors, applications. We saw an example of how we can all develop them, right? You can also make them in your company, but you need to make your organization ready for it. It's like we being ready for a television, we're ready for a radio, we're ready for a vehicle, car, and nowadays mobile phone, and so on and so forth, as an individual and as a family. Similarly, we need to be ready for these things also as an organization. So how do we do that? Importantly. So what happens is always early adoption is the best thing because it's going to happen anyway. The sooner you adopt, the more you have chance to get it right. That's important. What it means is, particularly in any of the industry, now think of it as industry. Remember, we showed an example of spiking neural network. We talked about how it's going to influence finance, fraudulency, and so on and so forth, right? So, particularly in some of these industries where we are, if you are part of it, if you're serving those industries, if you consider neuromorphic computing as an option, it will be even more better, like pharmaceutical, medical products, healthcare, space, construction. They're all the things essentially everywhere. Early adoption is even more important. But applications are coming to other industries soon. This doesn't stop here. So more industries, more opportunities are coming. What happens when you, in fact, there is a cases where you make an application for yourself that others will want from you to use it. That's how the excitement is happening because so many people are wanting to use it and adapt from you. So to position your organization, take your team for that matter, make your team develop something for your product, and for product need not be physical or electronic product. It can be the way you do accounts, it can be the way you do maintenance, and so on also. And then correspondingly reflect it to other department, share it with them, and slowly make it a part of an organizational culture. That's very important to think that way. Otherwise, what happens is we will be either isolated or we'll be falling backward, which is not required. So, neuromorphic computing is a considered potential. So, integrate everybody. So, think like a leader. So, how do you do that? Is first of all, like this is by the way, nothing to do with neuromorphic. It is there across the world, everywhere it happened, wherever somebody has adopted, includes our internet, includes our email adoption. Most of us, we have seen how things have evolved and you've also seen it. So how do you make something adopt and adapt is a very important part of it. So first thing is demystify the living intelligence for the entire organization. Don't make them think of these buzzwords and get scared. What is living intelligence? Nothing. There are gadgets everywhere you see measuring the data, measuring the conditions, and correspondingly we're doing cognitive computing to take some decisions, which means we can't just do randomly. Each of the decisions will have further influencing on part of it. For example, it can be as simple as at certain time, certain power and need not be done, it can be shut down. To certain time, some gates can be closed. Also, many things like that. So it's there everywhere, not in my which way. Now, how we can implement this, adopt this, so develop pragmatic scenarios for disruption and new value generation. So understand your industry, either your company or your business, either as a consumer, either a creator for somebody. What are the scenarios? Okay, identify some high impact use cases and get started. For example, when we did neuromorphic processor, what did we do? We did general processor, right? So what did we say? Let's think of some application. We don't just say you do your application of process is ready. We didn't say that. What we said is, okay, one of the things is radar-based human detection, audio scene classification, and then we wrote applications. At the same time, we were also experimenting with the data center. Don't forget that. That's a part of goes on like research. Similarly, you also think of some high impact use cases and develop it. Okay, and developing the things and correspondingly, it may need you to reskill yourself, capabilities, learning. All these are all important. Okay, do that, and importantly, ensure that we are ready as a company for any of the shifts in regulation, shifts in laws, shifts in other conditions. And so they're very important because a lot of these things, rules and laws are not made. So we need to keep an eye on that. Okay, I'm doing a new technology, but keep an eye on that, how the things will further evolve. Regulatory and those things are also very important. So when we started from the beginning, we said how neuromorphic is there here, but for instance, for neuromorphic, let's go AI comes, neural network comes, and then we say neuromorphic computing comes, and how each one is evolving, what are the options, devices, processor, applications, we kept on saying, showing you how it's possible. Idea here is to make you realize and be strongly feeling that, okay, this is going to be there. There is an opportunity to develop solutions right away. If I'm a developer, there's an opportunity to utilize them, planning to use them in my system if I'm a decision maker for me. And this doesn't stop there. For it to be done, you have to integrate your office, integrate everybody, take it to the next level, and so on. That's important. So having said that, there are imputable things. It's wonderful. Energy efficiency provide, architecture important. Okay, it makes your learning easy. They're all positive summaries part of it. Okay, and one more thing is to repeat that part of it. There's no standards here. There's a challenge. It's a problem because a new thing learning has to happen. That's a challenge. Early days, that's a challenge. But future is exciting. So when new things are happening all the time around us, you can see that happening. And you can so think of an application, think of a system, think of a solution, and you continue to do another thing. And multiple researches are possible. And what you develop in India for this, in Canada for this, in Africa for this can be used for across the world because one of those eras where technology is evolving, but at the same time, the application part of it is nowadays accessible to everybody. Almost all are similarly capable, but leaving the brain part of it. So it's a very wonderful opportunity for all of us to develop it. Now, there are a lot of references here. We'll use some more also to you for you to read. We talked about, and there are a lot more coming. Our request is just make a note. Suggestion is this one. You choose your, don't give it a start life like this. We'll continue to interact. My request is think of a project type thing for that matter. How I will think where neuromorphic computing can be used in my company or my product or my project. what is possible or what I can develop. Think of it as a project, an enabling project. Explore that, and correspondingly, we put something together and see how it goes. And that can be initial project. That's a good learning from the subject matter. Of course, we are always available, as I said, to give more. And sometimes, see, as we said, the idea here is to make it generic enough to introduce to people. Some of you would have possibly felt I'm too high at a technical, it's covering a very low. I would like to know more of the technology. Yes, we can definitely do that. Some of you would have thought so many buzzwords are there. How come you don't even know half of them? You don't need to. What's important is you as you realize that neuromorphic computing is among the realities game changing for the future. Neuromorphic computing will make sure you can do more efficient, intelligent computing possible. From the way it changes life at the lowest level, of course, it has to go a long way to go to the higher thing. It continues to happen. So let me try to utilize it. There are solutions available. I can start using them for development or for adoption and implementation. As long as you go with that, and let me map my learning, my understanding. Did I learn anything from it? Let me try by mapping it to my requirement, my company or my project or my home or my individually, what I can do for this. For example, okay, I've used my doorbell. What would be different if I have a neuromorphic enabled doorbell? Neuromorphic enabled camera. So if you think like that also for that matter, your understanding of this will go and corresponding can be done there. With that, I will pause here. Thank you very, very, very much for your attention and understanding. Thank you, sir. Any questions, sir?
Sir, like in this era, I think you spoke about it a little bit. What do you see as the major challenge for, you know, these kind of like neuromorphic uh, learning and development there? Like if you were asked like what is one major challenge, what is one main obstacle to make this bigger? You have a time horizon, I think in that map that you showed from Gartner, I think it's 6 years or something, right? Like in order to achieve that, like what do you see as one major challenge in, development in this
Yeah.
space?
Very glad that you mentioned that, because Gartner didn't quite say that, sir.
Okay.
What it said, if I made it understand that way, my failure, what it says basically is Gartner of any technology for that matter, it says is that that will be that likely time for it to be majority adopted. It doesn't mean it's not being adopted today. So it takes a ramp up, it takes a momentum, right? So what Gartner is saying is about 29, 20, about time frame is when you and I will become end users. Suppose we are saying all that. You say, wonderful, give me a doorbell. Suppose you ask me, what my answer? My answer is, sir, yes, there are customers with whom we are talking. They are making new doorbells with this one. For that to come into market, it will take a year, right? For example, like that. So that is so first of all, it is not then only, it is also a ramp up part. Now, the challenge part of it means typically we should think every technology will have a challenge, definitely. No, and a challenge and there's an opportunity, both. So what happens is, first of all, a lot of technologies came and vanished before they really picked up. Will this be one of that? Okay. Now, what is this? It is a microcontroller. Now, have microcontrollers vanished? No. The type of them are varied. It is there, right? But that kind of microprocessor, RISC, so many things are varying. It's all there. So microcontroller is required. Is our automation going to vanish? No. Alarm, signal, air, temperature, AC, securities, and they continue to increase more and more. And there'll be even how many sensors are in your home right now, your office right now, in your vehicle right now. And in your vehicle car, for example, there are about 20 sensors. About 10 years back, there were 5. Before that, there were none, for example. Like that. So when sensors are going to increase, the edge is going to be even more loaded. The processing has to happen more closely. It means edge processing will be the most defining one, and so processing will be required. And if we agree with that, the processor has to be more efficient, and hence neuromorphic processor will be very important. It will be there. What can change for that matter is currently spiking neural network is an algorithm we said, right? More important for it. We have seen so many CNN, ANN, we talked about Soma and so many things, right? So possible that some other better one can come. That's how it should be also, evolution wise. So the challenge is how quickly one will want to practice. In fact, if they think, as you like you said, okay, anyway, it's going to be like 6 years, let me wait, let me something to come. So if the adoption slows, it can slow down. That can be the challenge, the belief of it. As well, technically, it has all the potential to be a big one, sir.
Got it. So, sir, how do you compare this to? I think NVIDIA seems to have a different approach, right? They call it Rubin or something, which is
Very
not.
important. If you see, essentially ask one question, sir. In our life today, where is NVIDIA processor in our daily life? In our daily life, is there any application usage where it is being done or influenced or ensured by NVIDIA processor? We ask a question. The answer is, it is there, of course. Where is it there? For everything we are doing, it is there. Yes. Everything means, supposing you do something on the internet, anything you ask, anything, everything, it is there because currently it is in the data center, right? But ask the same question 10 years back, they were not in the data center, they were in the graphic card only, the most powerful graphic card only they had it, right? Courtesy, entirely Harvard people, not at all with them. If you realize the same thing can be useful for this, that's why they became big. Poor serendipity and God blessing. So now what happens is, even though they are there, their power, the sizes of the chip, the power of the chip, we are talking about what? Multiple watts, right? Hundreds of watts and so on and so forth, right? That because the purpose is at the aggregation level. You saw that slide we showed a sensor here in the data center there, right? They're all playing there, it continues to be there. This neuromorphic processor, whoever is developing, is on the leftmost, closest to the data source currently. Edge and other things. We also showed you an example, sir, where we said we talked about the data center, right? Still early days, we said it's going to be efficient, we said, right? Now, the data center of the old concept changed. There is also called AI data centers, right? Similarly, there will be data centers which will be more like cognitive data centers, maybe different in the particular scenarios, that is. So they will be using a neuromorphic more. It will happen. But NVIDIA chips and the graphic process and the neural network process and the neuromorphic process are not competing at all, sir. Hope I am clear.
Okay, understood.
In fact, this neuromorphic processor can actually make NVIDIA more successful because this is actually making more data come more faster, more intelligently, which means their data centers will be even more required. So NVIDIA will make more money because of these ones, not the other way around.
Okay, understood.
One question. Looking at the advantages and its capabilities that you have just mentioned, and the ability to respond in a very nanosecond of time. Do you think, because currently I don't see much uses of it, because currently maybe my the understanding around the different technology landscape which I have exposed to, it's more like cloud and AI and the quantum, right? That's where most of the time we hear the things. But the neuromorphic is something that I heard just a couple of class back when computing classes were happening. So in next couple of maybe next 10 years down, you think this is gonna acquire the the space where quantum computing or AI lies now?
If you see, sir, the question here is you think possibly things may not be evolving. Am I right in saying that? You don't see it
Yes.
here much. You mean the neuromorphic or you mean the edge? Or you mean the
I'm talking about neuromorphic.
neuromorph? The question, see, there's one thing, sir. How many of us use a mobile phone? All of us, right?
Hmm.
Our parents, how many of us know RISC-V or RISC-ARM, RISC processor? Right? No. So there was a processor, it became a RISC processor. That is called as ARM. That's why ARM is there everywhere in the mobile phone, right? Now, from that, it became a RISC-V, a open domain one that is there, right? So we don't buy a RISC-V processor or a RISC processor, or we are actually buying. We buy an Intel computer, by the way, that's correct. Okay, nowadays you buy a Snapdragon mobile phone, that's correct. But that's again, you're not buying a risk for. Similarly, what happens is we don't hear neuromorphic. You're right. Also, one more reason, sir. You're correct. You're not wrong at all. But that's how the evolution is. Because currently, wherever you see a detection, sensing, light, presence, doorbell, all those things, right, sir? When very soon, they're all based on electronics of 10 years back. And but in 3 4 years, that won't be sufficient simply because you nowadays itself we are buying a say take this camera phones, right? You have more intelligent phones. You take a photograph. Now we say we want to remove certain people in that, right? So what used to happen? It was not possible. I remember I'm the one of those people. I'm one of those people who doesn't send my photo. I try to edit it to make it as close to it possible. So I should take it to a computer, use other like MS Paint and delete and other things for that matter. Now, but currently there are mobile phone apps to edit the mobile phone photos there itself, right, sir? How is it working? They're all working on sorry, neural network algorithms, right? So more things are happening. So what happens is more intelligence needs to be required to address the data more accurately, more quickly, in a more efficient ways. So which means in future, neuromorphic processes are the way it is going to be required because not new neural network algorithms will require a processor. Simply put, when we want artificial intelligence means working like brain, which means processor should be working like brain, right? That's why it is going to be there. Now, you don't see it today. But if you see, that's what Gartner also is saying, right? What we are saying is that it is going to take about 2 3 years for you and I to have a product which will be in neuromorph. For example, at CES, as you know, the Consumer Electronics Show, last year, this year, our solutions are continuously be done successfully, shown well, and other thing, and so on and so forth. So currently, as it's already in the B2B mode, means you make it a neuromorphic solution tomorrow, you develop it, it goes to your business. But that will be part of a gadget which you and I will become to the consumer in 2 3 years. That's the progress happening, sir. You're right, but that's the progress. There's nothing wrong in that, isn't it, sir? So if you participate in it as a developer, as a user, as a creator, as a service provider, you will have a lot more opportunities open for you. So for example, in this case, you take the application kit from us, develop applications if you are into that space. Okay, I'm giving an example. Okay, and so that you're developing an application which will be required by somebody, some company, some device, some customer later. Because somebody is going to do it anyway. Why? Simply because we are looking for an ecosystem which has to function more close like brain, which means more processor like brain, as simple as that. Hope that gives an idea, sir.
Exactly, sir.
Again, as I requested, please feel free to contact me in it. I don't consider it, I think it's my failure if you think this is done. In the sense, you should feel comfortable that you can contact any time. Some of these aspects, some of you may think, you know what, I want to go to a particular neural network, I'll get the more detail. You know what, I want to actually go, but the shifting you showed, I want to go know to more detail. These are all fine. These are part of joy and learning and everything. Or I want some kids to develop an application, or I have some other. Please feel free. See? This idea of interacting and mutually learning, sir.
Hi, Prof. Can I just consult you concerning this technology? Based on your experience, how do the blind actually, it's in Braille system, right? How do the blind actually make sense of the world physically in front of them? And if there's such a technology that could translate by proximity sensor or whichever computing technology that could translate like what ultrasound does to the physical environment, the world in front, translate into a sort of a braille system where the blind could actually see in their mind's eye. Do you think it's possible?
See, first of all, if your question, sir, is about is that neuromorphic processing a sort of sensor dependent? Is that quite interpretation of your question, sir?
In a way, yes. Because I believe neuromorphic processing is probably one of the answers, if not the answer. But how?
So what happens is, see, it's a processor. What we did. See, the first thing, neuromorphic as a technology can be anywhere. One can make a specific technology-based processor also. For example, Prophecy makes image processor for cameras equivalent, which is neuromorphic enabled for that matter. Okay, that's the one approach. What we did is, so first of all, neuromorphic is a technology which can be made for an audio processor, video processor, or graphic processor. It can so on applications also. That's one aspect. Now, what we did is a processor which is essentially a generic microcontroller, which is independent of any sensor. Means you can think of any sensor, you can see how you can use this processor to make that sensor a part of the solution. So can be proximity, can be IR sensor, can be audio, any other sensor also. So in the sense, processor is not inhibiting or inhibited by sensor presence. Similarly, sensor also can use any microprocessor, but slowly, very soon, the sensor people will require that by having a neuromorphic processor equivalent solution, their solution can be more efficient and for the future generation. See, for example, currently all the automation solutions, sir, are based on electronics about 10 years back, understandably so. Like our cars have chips 10 years back, the technologies. What we talk about as the Bluetooth in the car is more than 10 years back technology. There are technologies which are very excited and working today, which will be in the car of 10 years later. So what happens is where the neuromorphic being more integral part of any of the solutions is going to happen soon. So it is not blocking anything. So if you have a sensor angle, ask yourself, am I making a sensor based electronics thing? Sensor is basically what gives a condition mapped to electrical signal. So that electrical signal processing, I need a processor. So can neuromorphic be one solution? If you ask like that, possibly the opportunities are now open a lot more for you. That's one of the ways of looking at it. Because wherever there's a sensor, signal has to be processed to make it understand. We in Inatera's processor for the microcontroller, which can be true for anybody, I'm not selling ourselves, is mapping the sensor signal to and a physical sensor is what maps physical signal to electrical signal. That electrical signal is not processable by all these aggregators on the other side, Intel, NVIDIA, and other people, Qualcomms of the world. So you need to translate it. So we are essentially translating that signal to and providing them. That's a processor. So we are actually enabling, in fact, increasing the sensor adoption, I would say. Hope that gives a clarity to an extent, sir. If it's not, let me know. You can also contact me later. Also, I'll definitely do that, sir.
Okay, thank you.
We will, of course, send this material along with other ones and so on. And please feel free to contact anytime also. Okay, sir?
Okay.
And the kits are available for people to develop, learn more and try. So researchers, for example, teachers, they can learn on this, play around, to get new ideas and other things, and that's a wonderful thing, sir. So, for example, recently we completed a 15-day workshop at IISc along with IIS professors about how neuromorphic research is going. Some of the top brains in the world have come and discussed and so on. It's a part of good learning for all of us, like that. The researchers can do it and do further. You can get new ideas possibly, like that. Anything more, or do we stop? I'm perfectly fine. I can be there all the time. I'm excited to talk to people, understand, learn, share what we thought of long time back itself and other things. So do we log out? If no further.
Yes, sir. Thank you.
Yes, sir. Thank you very much.
Pleasure.
Thank you. Yeah.
Thank
Bye.
you.
Have a good evening. Bye.
Thank you very much. Appreciate your
Thank you. Bye.
support. Appreciate a lot. Thank you very, very much. I'm always
Thank
at
you.
your service. Thank you.
Yeah.